Apologies for this. So all of the workshops shall be recorded and put online on YouTube. And let me start with a really short introduction to Adam, and then I stop. So Adam is currently an industrial PhD student at Lund University, collaborating with Zenseact, which is an autonomous driving company based out of Gothenburg. His academic journey began at Chalmers University, where he got his master's degree and was focused on monocular 3D object detection, and further worked in Zenvity as a deep learning engineer. And today, Adam's research is focused on reducing human supervision for perception systems in autonomous driving. So please go ahead.
Perfect. Thank you very much. Can you hear me and see the presentation?
Yep, all good.
Awesome. Okay, perfect. So thanks for the introduction. Today I'll talk about harnessing natural language supervision for autonomous driving, and maybe more specifically for perception in autonomous driving. And we're talking about natural language and perception. It's very natural to immediately think of CLIP, as was even already mentioned in the introduction. So I will give a very brief recap of CLIP. So bear with me. I'm sure all of you are already very familiar with it. But anyways, so CLIP stands for Contrastive Language Image Pre-training. And it's essentially a simple but extremely scalable approach for training a joint embedding space between images and text, essentially. So how CLIP was trained is that they scraped a huge data set of image text pairs from the internet. For example, like an image from a Wikipedia article with the corresponding text description of that. And then you train a text and image encoder to separately encode the two different modalities, and then maximize the similarity between the correct pairs at the same time as you repel basically the embeddings of all the other pairs. And this is very simple, but if you do this on a large enough scale, it turns out that you get extremely flexible models that both generalize across lots of different domains, and are able to do many tasks essentially zero shot without any specific training. For example, if you want to do classification, you don't need a classification label anymore. You can just take your image and compare it with the text of your different class names and just pick the class name that has the highest similarity with the image. For example, CLIP has been out now for a bunch of years and has led to lots of excellent follow-up works. Perhaps most notably, we have the generative revolution with like DALL-E 2 and Stable Diffusion and all these other works. The core of these methods is actually a CLIP model, or at least a model that's trained in the same way as CLIP was trained. So it turns out that this common embedding space of images and text is extremely useful for other tasks as well. And there have been extensions to CLIP. We have, for example, XCLIP, which takes CLIP to video. And we have MassCLIP, which is able to extract local supervision from CLIP. So essentially training a segmentation model to do any kind of segmentation here. For example, segmenting Batman versus Joker without ever training on that. So it's clear that CLIP is very useful. In autonomous driving specifically, you can use CLIP for lots of things. At Zenseact, it's actually the primary use we have for CLIP, or at least the most widespread use we have for CLIP, is the simplest one, which is where we use CLIP as a search engine. So we collect huge amounts of data, right? And then we embed, maybe not every single image, but with some sparse sampling. We embed our images into CLIP space and store it in a database. And then you can essentially have a search engine where you type in an arbitrary string and you are able to immediately retrieve the images that are most similar to that string, which can be extremely useful for collecting, if you want to collect a very difficult test set of some strange scenario that almost never occurs. It's hard to design a handcrafted trigger for that, but with CLIP, you can just write it. So here, for example, I did an example, a goat crossing the road, and then I searched in some subset of our data set. And these are the kinds of images that we get out. So it's not exactly a goat. I guess maybe there weren't any goats in this data set, but we have at least an animal crossing the road. Here we have a bunch of animals. Possibly it actually is goats. I'm not sure. It's hard to tell. But you have a bunch of animals, again, crossing the road. You get these stripes maybe looking like a pedestrian crossing as well. So far, so good. We have a cat here. I guess we were really running low on goat features in this data set. But all of these are, I would consider them all positive examples. We're able to find animals in the middle of the road. However, I also got this example. You might think this is construed, but it's actually, this is the first string I tried. So this is not really an uncommon occurrence. This was the first attempt I did. And then I got this kind of artifact, which is essentially we have a city street here with some lampposts in the middle of the night. And this bloom, I guess, looks kind of like a goat. And that caused CLIP then to say, oh, but this image actually looks a bit like a goat. So let's retrieve it as well. And that's obviously a problem. And if you don't agree, I took some artistic liberties here to enhance it. So at least this is what I'm imagining is happening. We have this image here. And then with the help of DALL-E 2, I was able to enhance it. And I guess this is what CLIP is seeing. And that's not really maybe CLIP's fault as much as a limitation of the camera itself. Cameras have some limitations. They're very sensitive to illumination. Obviously, if there is no global illumination in the scene, we get nothing. We get a black image. We can't work with that. If there's too much illumination, we get glare, or maybe even we get complete overexposure. And we also have these scenarios here where we have small localized, I don't know if there's an artifact with the lens or what's going on here, but this kind of blooming that can be disturbing. And that's a problem in general in autonomous driving. And that's why we typically have other complementary sensors, such as ultrasonics or radars, or perhaps most importantly, LiDARs. And that takes us very nicely to the paper I want to talk about today, namely LidarCLIP. So we basically had this premise that I just mentioned. We really enjoy CLIP. We use it a lot. We find it extremely useful. But there has some limitations, and we also work a lot with LiDAR data. So we basically realized that we really want a LidarCLIP. But we don't have any text LiDAR pairs, so we can't really train it from scratch the way that CLIP was trained. Maybe you could construct a small data set of text LiDAR pairs, but not this kind of huge 100 millions of pairs that were scraped for the original CLIP training. However, we have these huge data sets with LiDAR image pairs, which is what we get when we just drive around with a car that has both the camera and the LiDAR mounted. We get these pairs naturally. So our idea was to try to use these images as intermediaries, essentially. And the core contributions are, first of all, the method of encoding a LiDAR into an existing CLIP space, and then a bunch of evaluations to show that, first of all, this LiDAR encoding is actually complementary to the image encoding. So it's not just a straight up clone. This LiDAR encoding also is better than other prior works attempting to encode point clouds into CLIP space. And we can also show that we can use our LidarCLIP encoding for various off-the-shelf applications without any specific training or tuning. And the method, as I already said, is quite simple. So we take a pre-trained clip, we download the weights from OpenAI or OpenClip or whatever clip version you want to use, and we never actually update those weights. So the clip space is already spanned and it's frozen, and we don't change the space at all. Then we take our automotive data set and we design a LiDAR encoder. In this case, we use actually a not standard maybe, but we use an object detection LiDAR encoder, so it's not specially designed for this task. And we train this LiDAR encoder to mimic the image feature of the corresponding image pair to the point cloud. So in this case, there's no contrastive loss or anything, no negative examples. It's only the positive example of trying to mimic the image feature as much as possible. And again, we don't update the image encoder. And with this quite simple formulation, we get the LiDAR encoder, and then we can use this LiDAR encoder exactly the same way that the regular clip uses the image encoder. So for example, to do this kind of retrieval, we would have our text prompt, in this case, a dog on the road. We can encode it with our clip text encoder, and then we can encode all the point clouds in our large data set to create individual LiDAR embeddings. And then we compare those using cosine similarity and rank them and pick the best ones or the k best ones. And this works quite well. However, now we actually have no longer just two modalities in the same space. We still have the image encoder is completely valid. So we can actually use the image encoder to embed the corresponding images to each point cloud as well. And then we show that, we can of course retrieve using only the images. That's the standard clip approach. We can retrieve using only the LiDAR, or we can actually retrieve using the average embedding of the LiDAR and the image. And it turns out that these embeddings are actually complementary, and this joint embedding outperforms both the individual ones. We can also turn things around. flip them on its head and do zero-shot classification. So in this case, you take the LiDAR point cloud, you encode it, you get your LiDAR feature, and then you encode a series of different sentences corresponding to your different classes. So a car on the road, and person on the road, a cyclist on the road. You encode those using the text encoder, you compare the similarity, then you normalize it to get some kind of probability distribution. And that's essentially your zero-shot classification. And this again is something that CLIP does extensively in their original paper. We just showed that it also works for the LiDAR encoder. Something that was perhaps less obvious that it would work, but it does, is to use existing off-the-shelf generative approaches. Like, for example, DALL-E 2, they use CLIP under the hood. Unfortunately, we don't have access to DALL-E 2, but there are other similar open source alternatives. And we can show that we can actually swap out. So these either expect a text embedding or an image embedding, depending on if you want to do captioning or image generation. And we show that in both of these cases, we're able to swap out the expected embedding with a LiDAR embedding and create either LiDAR to image generation models or LiDAR captioning models. Again, without any fine-tuning or training, we just swap it into the existing approaches. And the quality of these is not exceptional. It's more maybe a proof of concept and a fun example than an actual sort of photorealistic, depth-consistent LiDAR to image generation pipeline. Okay, but let's look at some examples. So let's start off with retrieval. Here I just picked a couple of different prompts to just get a feeling for the capabilities of LidarCLIP. So here we can see if we ask for a tuk-tuk, we get something that's at least the first two ones look good. Maybe the third one is confusing. It's actually a motorcyclist with some stand in the back, I think. And then the fourth one is probably a complete failure. Perhaps it's because tuk-tuk is usually associated with tuk-tuk truck, and this one looks a bit like a truck van. I don't know. I would consider the last one a failure. Then we can retrieve for more global properties like busy intersection. That seems to work pretty well. As well as this bus stop. So overall, for the kind of simpler, at least, retrieval prompts, LidarCLIP works pretty well. So we try to push this a bit. And in the image, it's very easy to retrieve different lighting conditions, like distinguishing between day and night is completely trivial. But in the LiDAR, that's not obvious at all, because the LiDAR is an active sensor. It shoots out its own light and measures the response. And it's not apparent whether it's able to distinguish between night and day, for example. So we try to push it and ask for strange things. And as you can see here, it works often better than expected. So LidarCLIP encodes the intensity value of the point cloud as well. So there is some information coming back there that could give some hints, perhaps, of the global illumination. We try to compensate as much as possible for sort of biases in the data set. For example, maybe night images are usually empty. So LidarCLIP tries to retrieve mostly empty scenes when we ask for night. Doesn't seem to really be the case. But it also turns out that it works to some degree, maybe surprisingly degree, but it still works much, much, much worse than the image, which is what you would expect from just the nature of the LiDAR sensor. We try to push this even a bit further and see if the LiDAR can measure color. And it turns out that with these intensity values, it seems that the LiDAR can reasonably distinguish between a white car and a black car, for example, but it cannot at all distinguish between a red, blue, and green, etc. So it's and this seems quite reasonable with the fact that you only get a single reflectance value back. This was maybe more curioso than useful information. But we found it an interesting way to think about it, that we can use now this LidarCLIP to try to, with natural language, prompt the capabilities of the sensor, essentially. We did some quantitative experiments as well, comparing ImageCLIP, LidarCLIP, and this joint approach, where we just take the average of the image and LiDAR embedding. And it turns out that for object retrieval, LidarCLIP actually works better than ImageCLIP, which is perhaps a bit surprising since, again, it's only trained to mimic ImageCLIP. But if we do it on large enough scale, it seems that it's able to pick up stronger features. Maybe objects are more invariant in the LiDAR than they are in the image, and therefore it's easier. However, as expected, maybe also from the retrieval examples we saw before, retrieving the more scene condition kind of prompts like night, day, sunny, etc. In this scenario, LidarCLIP works significantly better than random, but much worse than ImageCLIP. Perhaps surprisingly, this joint embedding again actually outperforms the image embedding, but by a very small degree. Something that we believe is really useful in the retrieval category is our multi-prompt retrieval. And the thing here essentially is that we want to be able to retrieve scenarios that are extremely difficult for one of the sensors. So for example, a corrupted image of a nearby pedestrian. This is extremely important both for training, because maybe we can train the model to be able to sort of overcome this corruption if we can have a large dedicated training set with these difficult images. And it's also, of course, very important for evaluation, because we want to construct a targeted test set where we can see how does our model perform under extreme corruption or extreme blur, perhaps if it's raining, etc. However, just naively asking LidarCLIP or ImageCLIP for a corrupted image of a nearby pedestrian doesn't really work. If we ask ImageCLIP, it will give you either a corrupted image or a nearby pedestrian. And if you ask LidarCLIP, it has no idea about the corruption of the image, so it only retrieves nearby pedestrians. However, if we split it up so that we ask ImageCLIP only for corrupted images and LidarCLIP only for nearby pedestrians, and we then essentially take the average of these scores, so we basically score highly if the image is corrupted and independently there is a nearby pedestrian in the LiDAR scan, then we can get these kinds of images that we see in the bottom right. So here we have 3 pedestrians that are nearby, and the image is completely corrupted. You can perhaps see one of the pedestrians here in the image. It's feasible that it could probably have been retrieved if we prompted with a good enough prompt. However, the other pedestrian is completely invisible. And so this is an example of the very valuable training examples that we could retrieve with this multi-prompt retrieval. Now let's go on to other things, and I'll just really briefly need to show the LidarCLIP architecture to explain the next part. So as I said already, we base it on an object detection encoder, namely this SST, single stride sparse transformer backbone. And how it works is that we take the point cloud, we divide it into a bird's eye view grid, or these bird's eye view pillars, very standard stuff. Then we actually discard all the empty voxels and separate out the pillars into independent tokens. We process it with this single stride sparse transformer backbone. And then we get out a set of voxels with some high dimensional features. And then we run, similar to what CLIP does for the ResNet models, run an attention pooling step to construct our single global feature. And this is the feature that we use for training and the feature that we've used for the retrieval shown earlier, and all these things. However, after the training is done, we don't necessarily need to do this pooling step anymore. So if we just remove that and scatter our voxels back into the bird's eye view grid again, we actually have a bird's eye view feature map with local CLIP features. So a CLIP feature per voxel, essentially. And we were very curious to see whether these features are useful or not. Maybe, it's not apparent that the LiDAR encoder learns to really accurately localize their respective features. Maybe it just smears them out over the entire bird's eye view space. But it turns out that, at least in some cases, the local understanding is quite accurate. So here on the left, you see the point cloud, where we have colored the points corresponding to a given voxel if that voxel scores highly on the zero-shot classification of, in this case, a bike or moped. And you can see here that there are these 5, perhaps, or 4 hotspots correspond to the bikes. And if we look at the corresponding image, we see actually that there are 4 or 5 independent bikes here. So it's pretty neat that just from having global supervision, global 2D supervision, we're able to learn very local, accurate, open set 3D segmentation, essentially. This is, of course, as you may expect, a relatively cherry-picked example. It doesn't always work this well. And we actually excluded these results from the paper for this reason, that we feel that there is more work needed to be done here to really bring this to its full potential. But it hints at that there is something very powerful here. What we did do, however, to try to validate these capabilities somewhat at least, is to construct another zero-shot classification task, but this time based on the 3D bounding boxes in a dataset. So essentially, we took the 3D bounding box, We overlaid it with the bird's eye view feature map, and then we just took the average of all the voxels that happen to be inside the bounding box, at least partially. And then we get no longer a global feature, but we get an object feature essentially. And we run the zero-shot classification protocol as before on that object feature. And if we do that, we can actually compare with prior classification zero-shot point cloud classification methods. And it turns out that LidarCLIP works significantly better, at least in this automotive setting. These other approaches are more tuned towards model net and scan net and these settings where you have very nice dense point clouds around the entire object, which is not really the case for AD. So this was neat. Let me see where I am on time. Okay, perfect. And finally, let's just look a little bit closer at these generative applications. So like I said, here we just take existing off-the-shelf methods and we just swap the embedding that they expect, being a text or an image embedding, with our LiDAR embedding. And on the left, you see the original image with the point cloud here in the top corner. And if we caption it, we get, in this case, a white car is driving down the street, which is perhaps a reasonable caption. And if we just do an image generation from the LiDAR feature, we get the image here in the middle. There are some weird artifacts, but it's clearly captured the essence of this car driving on the street. It's hallucinated some trees in the background, and yeah, like I said, it's probably not like geometrically consistent with the original point cloud. And finally, maybe mostly for fun, we actually also generate an image which is guided both by the LiDAR feature and by the caption generated from LiDAR feature. So we basically guide with both the LiDAR embedding and this caption. And then we get a slightly improved generation. Here's another example, perhaps a failure case, where we have a person crossing the road. And if we just use the LiDAR feature to generate an image, we obviously get some person walking, but we've lost all the context. There's no longer an automotive scene. It's some abstract artistic rendering. The caption looks reasonable. And if we guide with the caption, we get something back that's at least a little bit more sensible. But you can see that the quality is quite bad. So there would need to probably be a dedicated future work to get this method to work really well, with some perhaps depth consistency and these things. So in summary, yeah, we propose LidarCLIP, a very simple way to connect LiDARs and texts and essentially extend the clip space to another modality. We show that it's complementary with ImageCLIP. We designed this multi-prompt retrieval where we query the image for something and the LiDAR for something else and use that to find these extremely difficult rare scenarios. We show that LidarCLIP actually is able to learn some local 3D features just from this global 2D supervision. And finally, we demonstrate that there's potential for many applications without a large amount of training and tuning. Just to wrap up, I'll show some of my thoughts on the future work. So like I already mentioned, many times, I guess now towards the end, we have only had this global loss where we average the entire point cloud and we average the entire image and we say that those two should be consistent. And that's inherited from CLIP, where we don't really have a good way of figuring out which part of the sentence corresponds to which part of the image. When we're talking about image and LiDAR, we have an extremely good understanding. We have our at least usually you have well-calibrated sensors, so you know exactly which point corresponds to which pixel. And that local correspondence is something that probably should be leveraged in a follow-up version of this work, where we can then perhaps get even sharper voxel-wise features. Also, like I hinted at, there are these video extensions of CLIP. It would be very nice to incorporate that with a temporal LiDAR encoder to be able to ask not just for static scenes, but perhaps for actions. Maybe we want to query for this semi-truck here, swerving across the lane, switching back and forth. Usually for autonomous driving, the actions are perhaps even more important than the statics of the scene. And finally, perhaps you're familiar with this extremely recent work came out a few weeks ago from Meta, which is ImageBind, where they use an approach that it's actually quite similar to what we did with LidarCLIP, where you freeze an existing clip space and you encode additional modalities into it. But they took it perhaps to the next level and encoded, I don't know how many it was, 7, or I think it's more than in this image, They encoded lots of modalities into the same embedding space. But these modalities are not really autonomous driving specific. They were more from like handheld cameras and handheld phones, etc. It would be very interesting to do an AD bind where we embed like radars, LiDARs, trajectories, maybe even satellite images, all the modalities that are relevant for autonomous driving into a single existing CLIP space. And with that, I want to thank you for your attention, and please feel free to ask any questions.
Excellent presentation, Adam. Are there any questions?
Yeah, sure.
One question, maybe you can relay it.
Sure.
It's about the use of do they use also the reflectance information? Not only the depth, but also the intensity that is provided by the language.
Did you hear the question?
I heard part of it. I heard it was about reflectance, but if you could repeat it, it would be helpful.
Do you also use the reflectance information that are sometimes provided by the LiDARs?
Yes, yes. Yes, we use the reflectance, and that's why we are able to, for example, differentiate between black and white, like I showed here in the retrieval. Without using the reflectance, we didn't try it, but without using the reflectance, I have a very hard time believing it would be possible.
My second question is about the resolution of your voxel nets, or I don't know what, your voxel-based network that you are doing, using to extract features. What kind of resolution do you use?
Yeah, good question. So we're using this SSD encoder, but they have a resolution by default of, I think, 20 by 20 centimeters. We enlarged that to 50 by 50 centimeters. So yeah, each voxel is half by half meter. So it's a rougher resolution than you would usually do for object detection, but still relatively fine, perhaps. It was mostly hardware constraints that caused us to increase the voxel size. We wanted to be able to train it. This model trains reasonably fast. On this, we train it on the ONCE dataset, which contains 7 million image LiDAR pairs. It's primarily a self-supervised dataset from China. And on this dataset and on 8 GPUs, LidarCLIP trains in roughly 1 or 2 days. In large part because we did this rougher feature grid.
Did you try to sample and pool, like for images, for example?
If we try to sample,
yes, instead of using one resolution like in images, I mean, sampling, pooling, and so on.
Aha, you mean in the LiDAR encoder essentially?
Yes.
Yeah. So no, we actually, I guess that's maybe the primary feature of this SSD network is that they argue that if they only do the sparsity and the attention is also there's also local window attention, that there's no need for these hierarchical backbone essentially. And it's a loose argumentation, but we chose this SSD network because it seems to be most similar to the vision transformer, which is used also in the original CLIP. And they argue that the vision transformer works much better than ResNet for this kind of for the CLIP objective. But we didn't evaluate so much with different backbones. There's no reason that there should be something magical with the SSD backbone. It's just the one we chose to use. So I believe like a typical perhaps second or some other voxelnet style network should work equally well.
So I had a really quick question, Adam. So really great talk. I was wondering if you have seen if the network is, so if LidarCLIP is sensitive to orientation and size, because you demonstrated color, and of course there are problems with it, but orientation, I mean, can I ask if I can get a car from the front or from the back? And it would give me examples of cars that are seen from the front or seen from the back.
Yeah, so we tried it a bit. It works mostly like the rough descriptions, like front or back, work pretty well. If you start asking for like if you give it a degree, it doesn't work so well. And if you try to explain the degree in language, then maybe it will work a little bit better, but
I see.
not too fine-grained, I would say.
Understood.
Yeah, Ravi, I have another question. This is Dimitris Metaxas for Adam.
Sure, go ahead. We have a couple of minutes.
Okay, so Adam, very nice talk. I just wanted to ask you, are you mostly interested in augmenting data augmentation? Because following up on Ravi's question, would you want to ask specific question like, for this car, can you show me other views? Or of course you can do the more generic that this clip type of architecture would be helpful. Like, give me cars, and as you showed. Is that your intention?
Are you asking about the generative approach?
Yes.
Yeah. So I think if we were to develop the generative approach properly, sort of actually start working with the generative network and try to make it generate something that's consistent with the points in the point cloud, etc.
Yeah.
And then I think it would be a very powerful data augmentation approach, because then you could start manipulating the points. That's very typically done in object detection, right? Where you like cut out the points belonging to an object and place it somewhere else, or rotate it a bit. And basically it's much easier to manipulate the point cloud than to manipulate the image. So
Yes.
I think it will be very powerful for data augmentation. But like I said, out of the box, what we showed right now, it's not really good enough. If you,
Yes,
I'm going the wrong direction. Like, yeah, you can see here that there are some weird artifacts. It doesn't really look completely realistic.
no.
So you would probably need to train a better diffusion model or something like that, and probably impose some.
Yeah, you're right. In general, though, I want to warn you that because I've done low GANs generation, GANs still do better, except it's a pain in the butt to train them. But with these methods, you may not get the best possible as long as the statistics you're producing are consistent with the real world, because you can produce something that looks nice to a human, but the statistics are off, and then you can have a problem if somebody wants to use it for other things. So that's the one area you should pay focus, because diffusion models to this day, they're not doing as well, but they're much easier to train, obviously, and to
Okay.
yeah.
And in doing as well,
I like a lot your approach. Yeah, we're looking at things like this, and you'll see my approach when I give the talk, which I could use points, for example, because we do use those. Yeah.
Okay. Yeah, I'm looking forward to your talk to see more. We have really not taken this data augmentation approach so far. We haven't dug into it at all, actually.
Sure.
So I look forward to hearing more about what you've been doing.
Okay.
It's a good question. So it seems like you're using for the LiDAR encoder just the two-dimensional input, right? On bird's-eye view images, or like from bird's-eye view for the LiDAR coordinates. Have you considered using three-dimensional encoders?
Yeah, so I guess it's not completely fair to say that it's two-dimensional, because it doesn't look at this as an image, right? It takes all the points in one of these pillars, and then they are processed with the point net essentially to create some kind of feature, and then after that you process it with this transformer, and I guess at that point it's two-dimensional. But this feature that's extracted initially is extracted using a three-dimensional point net. But yeah, I guess there's some trade-off. Typically, at least from the object detection literature, it seems to be a decent trade-off to do this kind of pillarization and then process the pillar with a small point net, and then after that treat it as 2D. But if there's no computational constraints, I suspect it's better to keep the voxels, maybe to have like some height layer with the voxels as well. It's just that the computations explode. But we haven't tried it.
Yes, one last question, Adam. I just noticed that it's an object detection based encoder. Does it make any difference if you actually use something like RangeNet or say, cylinder 3D, which are segmentation based?
Yeah, we haven't done those kinds of investigations, actually. We tried initially with treating sort of the entire point cloud with a point encoder, like a pointnet ++ or something, like very, very early stages of this project. And at that point, we noticed that these object detection encoders are very well optimized and they train very fast, and they just worked quite well for us. I suspect that there shouldn't be any real difference if you use a segmentation encoder instead. As long as,
I guess in a way you're putting a prior on the feature on the instances in the point cloud if you use this object-based encoder, right? So I'm wondering if you can query things like give me non-flat road, or give me a scene where the road has a hump or something like this.
yeah, that's a good question. I mean, you can definitely query for like weird structures, like you can query for a round statue next to the road or something. So it has some 3D awareness, but I think you're right that you're imposing a prior about things being roughly flat. And also you're definitely imposing a prior about some sort of size of interest, like this 1/2 by 1/2 meter. We're saying that anything that's significantly below that is probably irrelevant. So we actually noticed that we have a very hard time retrieving like small animals, like small dogs and these kinds of things are very hard to retrieve with our method because I guess the cells are too large.
I see.
Yeah.
Thanks. So in the interest of time, I suggest we take the questions offline into the chat, and it was definitely an exceptional talk. So we've lost 5 minutes into the next talk, but we have a longer coffee break, so we have time, so no worries. So thank you very much, Adam, again, for a great talk. Yep.
All right. Thank you.
See you. So our next speaker is Sebastian Huch. I'm sorry if I'm pronouncing it really bad. And he is going to present DeepSTEP, a deep learning based spatio-temporal end-to-end perception for autonomous vehicles paper presentation. So go ahead, Sebastian. It's your floor.
Thanks. Maybe I can take over the.
Sure. Yeah.
So in the Zoom, can you mute? Right, so everybody in Zoom can hear me?
Yep.
Okay, perfect. All right, good morning, everyone. So my name is Sebastian, and today I'm going to present our workshop paper that got accepted here at this workshop, together with my two co-authors, Florian here, and also Professor Johannes Betz. And our paper is DeepSTEP, as mentioned before, and DeepSTEP is short for Deep Learning-Based Spatio-Temporal End-to-End Perception for Autonomous Vehicles. And to start this presentation here, I will give you a short motivation how we came up with this concept that I will present in the following afterwards. All right. So what you will see in the next few seconds here is a short clip. So actually, our team, our lab was part of the India Autonomous Challenge where we participated. And the India Autonomous Challenge was a race series, or a still ongoing race series, where university teams are participating against each other. Every university team gets a car, as you can see here on the slide, a Indy Lights car, which was modified and has LiDAR sensors, radar sensors, camera sensors, basically everything you need to drive autonomously. It has the compute power inside, it has the actuation interfaces, so we can drive autonomously with those cars. And the task for the teams, for the university teams, was to write the software to drive this car around the oval track here. This is an example of the second race that we had in Las Vegas at the CES last year in 2022. And here you can see actually the final lap
between our car, which is on the left side here, or in the middle of the screen, and our competitor, which is overtaking us in the next few seconds. You will see something is happening there, and I will explain afterwards what exactly happened.
150-mile-per-hour speed, Polymove accelerating to the outside, 168 through the corners, nearly to 169. Now they crack 169, accelerating onto the front stretch, and a spin from Tomb down to the infield and able to continue on. No damage to the car, but what does that mean for Tomb? I think that is day done.
Yeah, so what you actually could see, they were overtaking us, and then something happened within our software, which led to our car spinning around, leaving the track, and then the race was over. So we were second, we got the second place. But I will explain in detail what exactly happened here. So what you can see here is the software that, or basically the software stack that we use here for the perception for this race. And basically we had some multimodal sensor data. In particular, we used LiDAR sensor, like the input point clouds and radar point clouds. And we did some detection and localization in parallel. So they were kind of decoupled. We will have a look at the detection because this was kind of the problem here where we made the spin and left the track. So basically what we were doing is we had the radar pipeline which generated our detections, and we detected some ghost objects. This is quite common for radar perception. In theory, nothing special. But then the problem began here in the tracking, where we actually tracked this ghost object for multiple time steps. So it basically what you can see here in the next slide is again a short video. It led to having a second track of a second car, which is actually going directly in front of our car. And this is what you can see in this short clip. So basically in blue is our car, we are driving, and in orange is the other car, which is overtaking us. We are tracking this quite good at this point, but as soon as we get the second ghost object, it basically directly drives in front of our car, and we were braking, and this led to a higher force than we could actually handle, so we made the spin. You should see it in a second here. So you see there are a lot of detections, the 2D bounding boxes, but at some point there are multiple detections on the left side, some of them from the radar sensor, the ghost object, and yeah, so we were spinning here at this point. And obviously, since we tracked some wrong objects, some ghost objects, this led to a wrong prediction, which followed up by wrong planning kind of, and then also wrong control, which led to the entire spin at the end. So here I have some key takeaways from this problem that we had here. The first is that the perception errors have a super high impact on downstream software. As you could see, there was some error in the perception, the very front section of our software, which led to us leaving the track. So we need some kind of reliable software, especially in the perception. Second point is that our sensors were kind of decoupled. So we had the radar pipeline, we had the LiDAR pipeline, they were kind of not communicating with each other, because we had some kind of late fusion and not something like an early fusion or mid-level or feature fusion. So having some kind of intelligent sensor fusion could, in theory, handle these situations. The third one is that manual tuning is error-prone, which means we had this tracking, which was done by a Kalman filter, and we tracked the object for multiple time steps. This time step is a handcrafted, like the number of time step is a handcrafted number. So this is, yeah, obviously error prone. So something that could be learnable could avoid such problems. Yeah, since we saw there were some problems in the beginning here, we took a look afterwards at the state of the art. What could we do better for the next time, for the next races, and also for the real world outside, for the road application. So we looked up what could we do in the area of AV perception or end-to-end perception for AVs. There are a lot of papers, all of them are some kind of connected, but then again, we looked at some very specific points which are valid for the object detection and also for the mapping, because those 2 points are actually the stuff that was decoupled before, and we want to combine them. And in the current research area for object detection, there's always the huge discussion between 3-dimensional input space or 3-dimensional processing versus the bird's eye view. This was also the question that I asked before in this previous session that we had here, if people are using 3-dimensional inputs or bird's eye view input. So this is always the big discussion. And the second one is if people are using only a single modality and processing it up to the end until you get some objects out of your pipeline, for example, only using LiDAR points, processing them until you get the object list, or if you directly fuse them with cameras or with radar point clouds, for example. This would be the multi-model approach. Then for the localization or for the mapping here, there's always the huge discussion if you should go for mapless approach or if you need to use HD maps. There's actually a workshop going on, I think, in parallel right now about this topic here. And what also comes into play here is a part of scalability. Obviously, if you need to use HD maps, they don't scale very good. So this is a very big problem here for if you go with the map-based approach. But then we found one network which works quite good, or which covers some of the topics that we previously had problems with. And this is the BEV fusion network. Probably some of you people heard about this network. This was published last year at CVPR. And what they are basically doing is they have 6 camera images as an input here that you can see on the left side. They cover 360 degrees all around the ego vehicle. Then in the middle here with the black background here, you have the LiDAR point cloud, which also covers the entire 360-degree horizontal field of view. And those are the 2 inputs. And then what they are doing, they are projecting this into the bird's eye view. I mean, for LiDAR point clouds, this is quite simple. But then for camera, they need some kind of pre-processing to project this into the bird's eye view, all of the 6 cameras. Then they extract the features out of the bird's eye view camera images and out of the bird's eye view LiDAR point cloud and generate 2 outputs. Basically, they have 2 different perception tasks, which is the object detection, obviously, as you can see here with the orange boxes, the blue boxes, and so on, to detect all the traffic participants here. And also on the right side, the output is some kind of lane information, what the actual environment looks like around our own ego vehicle. So this is a quite nice approach, but then there was something missing that we thought of. So our research gap is as follows, that we want to generate a end-to-end perception pipeline, which uses multi-model data. So BEV fusion was using LiDARs and cameras, and we were thinking of using also radar sensor, because the radar sensor has a nice feature that it directly gives you the velocity information of the detected objects. It can directly measure the velocity, which is quite nice. So we want to integrate the radar sensor, which also has a kind of similar representation as the LiDAR sensors. It comes in point clouds. The second one is that we want to integrate the temporal domain. We also heard this in the first session here, that the temporal domain is something that people are working on. So the problem is that usually like the networks start detecting an object in the current time frame, but then they kind of have to do this again. They start from scratch in the next time frame, so they're not kind of having this temporal domain integrated into their sensor fusion, and this is something that we want to cover. And the last thing is, I mentioned this before, and this was something that BEV fusion is already doing, is that they have task-specific modules and they can communicate. So basically, the object detection is never decoupled from the localization, right? So if you imagine if there's a car on the road, it's basically, for example, the heading of the car is basically based on the lanes, on the orientations of the lanes. So those 2 tasks are not decoupled, but coupled. And this is what we want to integrate in our approach. So on the next slide here, you can see a short overview, a high-level overview of the pipeline, and we will go into detail what we think about the different modules that you can see here. So basically, as I mentioned before, the input is multimodal sensor data from the 3 modalities, camera, LiDAR, and radar. Then we have our deep fusion network here in the middle, where the kind of magic at the end happens here. I will go into detail on this on the next few slides. And then afterwards, we will have our task-specific perception heads. We will focus on the detection and on the local mapping, but you could think of adding another task-specific detection head, for example, like for traffic sign detection, traffic light detection, and something like this. So we will focus on the object detection in this case. At the end, once we have the detection and once we have the local mapping, we will combine this in some kind of environment representation and use this environment representation for the following tasks of the prediction, of the planning, and the control to complete this autonomous driving software stack. But in the middle is DeepSTEP, and this is where we will look into detail right now on the next few slides. Starting on the left-hand side here, we have the LiDAR point clouds, 3-dimensional point clouds here in the beginning. Then in the middle here, we have our radar point clouds, which include the velocity information as well, but they are still encoded as point clouds here. And on the lower side, we will have camera images also covering the entire area around our own vehicle. Those are the two-dimensional projected images as you know them from normal cameras. Using those raw sensor inputs, we will encode them into some kind of latent space, as you usually do. But we will also use, similar to BEV fusion, the bird's eye view that we will use to encode this into the latent space. For LiDAR point clouds, this is quite easy to convert them into the bird's eye view. And also for the radar point clouds, because the input is quite similar, it's just way more sparse than the LiDAR point cloud. For the camera images, the projected two-dimensional camera images, we have to reproject them into the bird's eye view. So this is some kind of pre-processing step that we need to integrate here. But then once we can extract the features from all the three different sensor modalities, we get the latent spaces from each of them, we can combine them in the next step here. And there we can combine them here in our deep fusion network, where actually we combine the latent spaces, not the, so this is the feature fusion and not the raw data fusion. And also here, as you can see here on top, is basically where our recurrent operation takes place, where we will integrate the temporal domain. So basically, the features from the previous time steps will get incorporated in the next few time steps. So the network knows like what happened in the last few time steps. So then we have our shared latent space, our entire features, and from there we can again decode this into our perception specific tasks for the detection, or for example for the local mapping. Those two tasks we will focus on. Afterwards, as I just mentioned, we will just create some kind of joint environment representation. Yeah, so this is our entire architecture. I will display this here again in on the entire slide here. Basically, yeah, we have our inputs here, our three-dimensional sensor inputs from the three sensor modalities. Then we have our representation, our output at the end, and in the middle is basically where we extract the features sensor-wise, but then combine them in the deep fusion network and also include the recurrent operations here. Afterwards, we'll have our perception outputs here using the detection or the local mapping. So there are some next steps. So this is basically our concept that we have in mind that we are currently integrating. And obviously, since this is a data-centric approach, we need a lot of data to train this. But there we have a very nice research vehicle at our lab at the TUM in general. On the top right, you can see it, which is equipped with all the sensors that you need, cameras, LiDARs, radars, and much more. So basically, we will use this vehicle to generate data sets. We will also want to open source this data set quite soon. And once we have this data set, we can obviously use it to like train our network, validate our network, but also we want to use this in a real world application. So basically, what we are doing with this vehicle here on the top right is to use the AutoWare software to apply AutoWare on this car, but then we want to check how our software, how DeepSTEP performs against AutoWare, where we can basically just exchange the different modules here. So this is the goal, that we can drive with this car on a real world application in Munich. But obviously, we also want to benchmark this on some common public data sets. There's some potential using our network that we thought of. First of all, and this is the most important, it will reduce the complexity. So obviously, the network itself is quite complex, but the thing is, we need fewer modules. So at the end, we don't need first like the object detection, then the local mapping, and the localization itself, and the tracking, and so on. So this will be combined in a single network itself. So this will reduce the complexity. The second point is, since we are leveraging the temporal domain and also the multitask, multiple tasks basically that we will cover, multiple perception tasks, this will generate some kind of scenario awareness. This was basically the thing that I explained before, that for example, a car which is located, like usually cars are located on the road, so we basically know where the road could be and vice versa. The cars are not located offside of the road, so the mapping kind of learns from the object detection, but also, yeah, as I mentioned before, vice versa. The last thing is, which is also quite important for us, since we have this research vehicle, and basically, like we had to fit this research vehicle with all the different sensors, but there are actually no publications on how many sensors do you need, like where to place them, do you need 360-degree coverage from all of the sensors, or is it possible to only have 360-degree coverage from only the cameras and then complement this with only a front view, a LiDAR sensor, and so on? So what we were doing is we were going into simulation, simulating some field of views and so on. At the end, we ended up with like having 360 degrees for the entire car, for all the 3 domains, right? This makes probably no sense, but it's nice to just generate some data sets where we have the coverage for all the 360 degree for all the 3 sensors. And at the end, we can do some kind of sensitivity analysis. So what we can do is basically use the entire data set, but then also, like, for example, do some ablation studies where we only use the front LiDAR and like turn off the side LiDARs, for example, or the side rotating LiDARs that we have, to see if we actually need all the sensors or which sensors are actually needed. This is something that we definitely want to do afterwards. And this is enabled by using our DeepSTEP approach. So in summary, like, the DeepSTEP is still a concept, so this is still work in progress. We are on it to implement this quite soon. So DeepSTEP is a spatio-temporal deep fusion network. It builds upon state-of-the-art, as I just mentioned before. For example, the BEV fusion approach is quite similar, but we want to integrate more things, like using a temporal domain or using, for example, a radar sensors, since they also have quite valuable information for the sensor fusion. Yeah, as I mentioned before, it is currently developed, but we want to generate data sets and also apply this at the end in the real world. Yeah, thanks for your attention. So yeah, this is us here. The guys are also sitting here. So if you have any questions, feel free to ask us right now, or as well afterwards, after this session here. Thanks a lot.
Do you want to replace the pair of successive acquisitions point cloud with the radar? Because in your architecture, I didn't see that you are processing in parallel current frame and the previous one to provide the temporal information, speed information.
So, sorry, say that again. Like, what exactly?
You mentioned about temporal integration of temporal.
Yeah, exactly.
On what is based this temporal?
Okay. So basically, the input is usually just one point cloud from radar, one point cloud from the LiDAR, and like 6 camera images, for example, right?
Temporal rely on the radar.
Yeah, and then initially you just have this one frame from the radar, for example, but then we will process the single frame. This information will be stored in the deep fusion network, right? But then in the next time step, you will get another frame. We will also process this single frame, and it will be kind of combined with the information from the previous time step. So this is how we want to incorporate the temporal domain.
The problem is related to the radar. They are not too reliable.
Yeah, depends. Exactly. Yeah, this was what this was the problem that we had before, right? With the motivation that I started. But this is exactly what the network itself should learn. So if there's a false positive object, this is in theory no problem, because if it only happens once, it will probably be disregarded, and it will not be forwarded to the entire output for the prediction, planning, and control, right? If it happens in multiple time steps, yeah, this is a problem. But then since we are using multiple sensors, we are not only using the radar and like processing the radar itself, and at the end, like fusing this in the late fusion, we are doing some kind of deep fusion. So the network should learn that even if there are false positive objects from the radar, for example, then we can basically filter them out, or the network should learn to filter them out by just looking at the information from the cameras where you shouldn't see this object, or from the LiDAR where you shouldn't see this object. So this is something that should be incorporated within the network, even though if there are some problems that we had before in the motivation that you saw, because they were running in parallel and not actually fused at some point, or just fused in the late fusion, but then it was kind of already too late. Yes, please.
The first movie that you have shown was about autonomous driving, but when you were using here, exposing end-to-end perception, but not end-to-end driving, right?
Yes, correct. So
there's planning and control.
This is
modules.
Exactly. So in our approach, this is just about the end-to-end perception, which basically starts from the raw sensor input and ends at the outputs from the perception. And this incorporates the detection and the local mapping. This is why it's end-to-end. Like it combines also the tracking. What is not combined is the prediction, planning, control. Those are still.
This is why I understand why did you do this sudden braking because of those obstacles. Usually we perform also obstacles prediction over time, and then risk assessment, blah blah, and the planning. How come that you just went down just because of one single obstacle?
So the problem that happened there in the initial video that the people just saw was that basically, like, we had this false positive object from the radar, and we actually had it over multiple time steps. So if we only have it once, that's no problem, because then we will disregard this in the following prediction and in the tracking, basically. But we had it for multiple time steps because of some kind of reflections from the wall, from the racetrack wall. And this false object basically had a different yaw angle than the actual vehicle that was driving in front of us that just overtook us. And since it had a different angle, it was kind of heading towards our own trajectory. So we were predicting this object to cross our own trajectory. So at this point in the planning, we were thinking of, okay, there's some object crossing our own trajectory. If this would be a real object, it makes sense to brake, right? So but at this point, we didn't knew that this is not a real object or
just remove the radar.
Yeah. Interesting question. But the thing is, the radar actually helps us because it gives us the velocity information. The other one, you can retrieve the velocity, but still, we were driving at 270 kilometers per hour at this point, and our range is quite limited for the LiDAR. The range was about 80 meters for our detection. We were using a clustering algorithm there, and also a neural network. But then you only get a very few points because there's also the banked angle on the racetrack where you have to kind of look upwards. This is quite challenging for if you would only use the LiDAR sensor. So we used additionally the radar sensor because the range is way higher. So we could get detections from the radar sensor of up to 200 meters. And the very nice thing is with the LiDAR sensor, if you only get a few object or only a few points and you classify this as an object, that's quite nice. But still, you cannot track this over time because it could be some kind of false positive objects from the LiDAR as well. We had many of them. But if we complement this with the radar sensor, it gives us the velocity information. If we fuse them together, we directly know from the very first detection of the LiDAR that this matches with the radar detections that we had before. And then we can like track them over time because like we have the velocity information, we can kind of integrate forward where this object would be in the next few time steps. And this is how we could fuse them. Otherwise, we couldn't fuse them.
So, excuse me. So, in the interest of time, I suggest we take these questions offline because we again are overgoing time limit for the talk. So, I would like to thank let's thank the speaker again for a really intuitive presentation. We do have questions for you. Please write these questions in the chat or directly contact him during the coffee break that's coming up.
All right, thanks.
Thanks, Sebastian. So we have our next speaker that's coming up. This is Professor Dimitris. Are you able to share your screen?
Yeah, let me share my screen. Yeah.
Okay, in the meantime, I'll just give you a short introduction. So Professor Dimitris Metaxas is a distinguished professor in computer science in the Department of Rutgers University, and he is directing the Center of Computational Biomedicine, Imaging and Modeling, and the NSF University Industry Collaboration Center, Qatar. And he works in the area of AI and machine learning applied to computer vision, dynamical systems, and environment and medical image analysis. So the floor is yours, Dimitris.
Yeah. Thanks a lot, Ravi, for inviting me. So you heard from all these nice talks before that are primarily data-driven, right? So what we're trying to do, based on my experience for a lot of years, is that if you couple data-driven with dynamical systems, means with models that obey ODEs, which of course you saw with your analysis days, then you can do much better understanding of what's happening But not only that, but introduce, for example, you will test your system, you can introduce on the fly objects or obstacles you've never seen. And the system works because you have an ODE now. So what I'm going to start is I'm going to start talking to you about first the perception part, right? So what we've done before since 2 years ago, about 3D object detection and motion analysis with dynamic modeling for improved modeling of coupled dynamical systems, as I said, cars, scooters, pedestrians. And to do that, there are 3 parts here that we want to do 3D object detection, including out-of-class objects. That's the vision part. And we want to do real-time performance, and we want to use this as input in a dynamical system. We'd like to couple and make an end-to-end system so that we can understand what's going on and not always depend on so many data that there are never enough, which to me is the problem why we cannot have autonomous driving. There's always going to be a case with lighting, etc., that's going to be problematic. So towards this, we started working on 3D object detection. We did use LiDAR plus cameras. So, but a problem that many of you talked about is this out-of-class detection. Well, you train on data, right? Something happens like a wheelchair and on the road, look, you don't want to basically ignore it and then hit the wheelchair. So what, for example, in RNNs at the time, I mean, these days, of course, you do transformers-based methods, like all these diffusion methods, but doesn't mean they'll work better if you don't have a lot of data. So for cases like this, right, how could you solve that? So would like to do motion prediction also, because movement is extremely important. If you don't understand how things are moving, you cannot avoid obstacles or you cannot avoid potential accident. So I'm geared more, because we have funding here in the US for this, more towards avoiding obstacles and saving lives by avoiding accidents or predicting accidents. So a big thing is not just to model things, but also to do prediction. So we would like to use bounding boxes, even though these days, I mean, there are networks can do 3D. But most important is the bounding box, so you understand what's in the bounding box. And occupancy grid map, so you can do discrete map over a 2D plane if things are on the ground, of course. And then we can encode a certain grid cell which is occupied, and no direct correspondence among cells across the image. So this was the state of the art, and still is difficult to mold object dynamics. So first I'll show you what I can do with vision only, data only. So basically, we want to jointly perform perception and motion prediction, which is a precursor, as I said, to using ODEs afterwards, coupling this with ODEs. So we'd like to aim to better capture the motion of objects beyond the training data set. So the input is LiDAR, point cloud sequences, and the output is the category of each grid cell within bird's eye view. And there are 2D motion vectors. Of course, these days you don't have to do bird's eye view, you can integrate with other cameras. But it becomes increasingly difficult. How are you going to put a ton of cameras? And, there are issues there. So this is the LiDAR, right? And the bird's eye view map with motion and category. So basically, I know it's cars, I know it's pedestrians, because I'll show you afterwards what I do. So there's been some prior work which from in ACCV 2020 that talked about how to voxelize LiDARs and how you do motion planning. And our method was motivated by this, but what we did is we do synchronization, discretization, spatio-temporal pyramid network, like a precursor of transformers, cell classification, motion prediction, state estimation. So the step one is ego motion compensation for the input sequence. So no ego motion, you see things wrong. Basically, this is the correct way when buses are changing. So on bird's eye view, right? then so bird's eye view map representation, so you have maps, right? So what you do is you have this neural net where basically based on the baseline method we discussed before, that the motivation, so we can do basically correspondence between where things are and where they are, bird's eye view map. And then we do spatio-temporal shape feature learning in the hierarchical way. So it's a spatio-temporal pyramid network, only rely 1D and 2D convolution, very simple, very efficient. You know, if you want to do what I've learned in practice, if you want to do things and apply them, they better be simple, and they don't have to use, you have to use vanilla, for example, diffusion methods, or even though they may be better in some ways, at the same time, they're very costly, right? So the question is, if you want to deploy in a car, for example, because during, as I'll show you, these are very fast methods. You have to do that. So, and cars have GPUs, like the high-end cars. They do have this kind of methods. So basically, using this now spatio-temporal approach, we can train, you know, in a spatio-temporal way, consistently the losses of, you know, tracking objects. If you do that with some post-processing before suppression, after suppression, then in our experiments, you can see our method runs at 53 frames per second. We've improved it actually even since then. And we do a lot better in most of the time with speeds less than 5 meters per second, speeds greater. And they get much better actually at higher speeds. And classification anchors, you see, it's pretty good. So, and you can see below what's happening, right? Without ego motion, with ego motion, right? And then you can see now, here's the question, why? This is the introduction, right? Because we use these methods plus other methods we can extract 3D. I mean, this is not so complicated to do if you have good bird's eye view. And if you have these trajectories, like point trajectories, or if you want to put the whole car as trajectory, but the important thing is we don't have position, we have velocity. Well, how can I use that now and then put that, associate these findings now with the dynamical system so that I can do prediction? I mean, you can do simple prediction, you can put Kalman filter here, but these are, as you know, Kalman filters I've used many, many years ago, even my thesis in the 90s. But problem is they work well assuming Gaussian noise, etc. If things are non-linear and non-Gaussian, then what are you going to do? Then you have the excellent Kalman filter, then there's no guarantee. Of course, neural nets are not guaranteed, but if you encode an ODE in there, as you're going to see, it's much better. So, how do you couple the adjoint dynamical system modeling? We'd like to learn interacting dynamical systems. Why? Because there are cars, pedestrians, whatever. And it has a wide variety of applications, autonomous driving, human-robot interaction, urban data mining, there's a lot of things. So given the input, as I said, I have points and the state, basically, the system, which is position velocities. And I want to estimate futures. So I'm going to do prediction now, but prediction much better than just a data-driven approach. And not only that, but I can start studying relationships, because as we said, if you have LiDAR, of course, you can see relationships in terms of velocities and position. It's very important if you want to understand, is there going to be a collision? You want to understand, of course, the distance between objects. Because if they're too far away, there won't be any proper collision, right? Even if they're coming towards each other. But if they're close, it's a warning. Like 20 years ago, I used to model these things explicitly by hand with very complicated dynamical systems. And of course, they worked well, but you know, they were not so generalizable as with these methods that you're going to see now. So the challenge is, it's a multi-model nonlinear problem. So the agent trajectory, I said, assuming you have it from the previous methods, have very plausible intentions, interactions, goals. So it's not as simple. to say, okay, I know the points, but how do I know what they're going to do without prediction, right? So the obstacles are static, dynamic, sudden, not in the training data set. So a big problem for autonomous driving is interpreting things that you've never seen before. And how are you going to do that? Just data-driven is not enough. So we need interpretability. We like to compute interpretable agent trajectory solution in the presence of other agents and obstacles. And of course, interaction models, agent to agent, agent to obstacle interactions. So like in this case, so how are we going to do that? So previous methods are mostly data-driven, as I said. So agent interaction, model use graph, social pooling, spatial transformers, you know, a lot of this well-known and you know, working well methods, but they fail to learn the underlying continuous temporal dynamics. If you see how everybody uses, that's because of the limitations of the data, is that they try to do spatio-temporal, but it's per frame usually. What if I want to encode the dynamics of the system in a continuous way, end to end? And how do I want to model explicitly agent interaction so I understand what's going on as opposed to the network, which doesn't offer much understanding? So this is a discrete state transition. Well, I want to do a continuous. So only ODEs can do that, right? So how do you model an agent trajectory, relational and temporal dimension? Relational means spatio-temporal, right? So I want to model the temporal dynamics using our ODEs to learn continuous temporal dynamics. And of course, we can move to PDEs, but then it's more data, so it's a little bit more complicated. So I would like to model agent interactions using two variables, distance and agent interaction intensity. Why is that? Because I want to learn how aggressive is one driver, or for how passive is one driver. You know, there's all sorts of driving, and I want to understand this. Effective agent trajectory control without retraining. Well, you have a car, right? At some point, if you want to be autonomous, you have to go back to what should be after, let's say, avoiding an obstacle. Well, how do you do that? Of course, without colliding with other nearby obstacles, but at some point it has to go to where it should go, right? And of course, we have done some extensive experimental study for this. So ISO is our system, interacting system, or is an encoder-decoder architecture with transformers. But what the novelty here is we built and solve ODEs in latent space. So basically, I control the latent space of the network. So in real world space, we built, so what I've done before, which was very amenable to neural nets, except that we couldn't do it at the time, was like we did by hand. Like you have the state of a vehicle, and of course it applies to many vehicles. Position, velocity, let's say, and the environment. The environment is targets and obstacles, and of course noise, because your systems are not. That's the old style modeling, right? But the weights are also dynamical systems. I mean, that's the ultimate, if you want, in you know. I started with well, my name is misspelled here, but I started with you know, in AI some publications. We work also with Leo Gibas because he has this dynamic data structure, so we can keep up as you're going with what's close to you. And we did it in more robotics conferences. But this is the fundamental contribution we have. Now this approach, we can convert this into neural nets. So how do we do this? So let's say with the previous visual system I have, and I'll show you a lot of real world situations because we have a lot of grants for this. So the input is trajectory to sensor-based interactions among agents, right? So you estimate those. What you do is you encode, let's say, several points that you've seen in the past, because you know the PDEs of the past were Markovian of one state before, right? So you assumed, as you solve the PD, you assume all the previous states are encoded. But with neural nets, I don't have to go Markovian order 0. I can go many steps before. Let's say 5, 10 steps. I encode them into one point, and then I solve an ODE in latent space. And then I convert the solution of the latent space into real space. Okay, and then if you do that, then for each trajectory with known points up to time, th, let's say, we encode the points with interactions from other agents to a single point in latent space. That's the encoder. And then use the encoder input as the initial value for each agent in latent space. You pass it through the encoder. And then in step 3, model agent-to-agent interaction, use multiple ODEs, and each ODE to compute latent points in future time steps. Ravi, I have till 3 o'clock, right? I mean, 3 o'clock my time, and whatever is 10 more minutes, right?
Yep.
And then we decode the latent points into real world position and velocity information. So this is the decoder. So basically, we do initial trajectory. I'm giving you now a little more details here. So encode the historical trajectory for each agent into latent space. I just want to show you that I will do spatio-temporal. Basically, not only the position, let's say this position, but the position with respect to others, that's spatial, and of course over time with everybody. So that's the new thing which you can do with the network. So you can blend basically the dynamics of everybody. So basically this trajectory is affected by neighboring trajectories. So that's why I want to do coupling, right? So encodes the spatial relationship at this time step, temporal, encodes state, and you put them all together, right? So decoder generates latent trajectories and decodes the latent vector back to real world space. So that's the idea here. So let me tell you something. So, but for every agent, the model agent interaction with other agents and temporal dynamics latent space. So remember now, this is data driven, right? It's not like I made up some dynamical system. I'm learning it, but I'm learning the dynamics and the dynamics of interaction. So if H is the latent space state, of course, the change of that is going to depend on the current state plus interactions, and those are measurable and convertible, right? So encoded features of states at time t, and then distance interaction intensity, agent to agent interactions. I'm trying to find now how intense, how important is how close are they coming together? I mean, is this dangerous or not? I want to learn it all. And the decoder moves in temporal dynamics. So it computes how an agent J affects the dynamics of agent I and the distance between agent J and I. And agent interaction intensity are multiplied to compute the agent interaction here. Okay. So what can you do? Now I want to control, because let's say, autonomous driving, I have to have goals, right? I need to do them, right? I need to ensure. So in latent space, I cannot control. So basically, if you see here, if I want to go, if that's what the projection is going to be without obstacles, or this is my goal, I want to go here, basically. But obeying the rules of the road, right? I cannot just go from here to there, right? Straight line. I'll show you an example of how this happens. So that's where the control comes in. So if it's a repel, if it's an obstacle, I want to go, of course. I mean, if there was an obstacle going towards me, I want to avoid it. With, of course, other constraints from the environment. And let's say I want to go to a desired trajectory. So you can put, all I'm trying to show you is a lot of controls there. Okay. And it's within your natural this time. Okay. So, for example, so I can control an agent to avoid obstacles and or agents by modifying the agent's ODE in latent space without strain. So if a car is autonomous, it has to make decisions, right? I want to go from A to B. Let's say it follows Google Maps, but it has to deviate and go back, right? With, of course, constraints from the road. You don't want to go on the sidewalk, for example. So all this is how we can do that. I'll show you actually in real world what's happening. So we did get data from German highways. They're very good bird's eye views, and they have a lot of cars, pedestrians, scooters, etc. They don't have much occlusions from drones. And of course, we have our own from Asbury Park in New Jersey. What we do is of course, we perform all data-driven methods. That means no surprise to you. So based on the average displacement error. So the moment you put a model and you can control the model, of course you win. So the question, what wasn't before, and that's what I'm pushing all my career, that's what I've been doing, model-based learning. I mean, if you know something, or if you can model something about the world, you have to put that in your learning. Because if you don't, the world is way too unpredictable. And you cannot never have enough data. And of course, I liked a lot, of course, the previous talks like augmentation, etc. I mean, we can do all these things. But at some points you have to understand what's a car, because a car has different constraints in terms of speed versus a scooter versus etc. So I should always perform best, which means I should can deal better with different trajectories. This is collision rate. We're introducing suddenly an obstacle. Where we definitely make a difference is like if I use data-driven approach only, I mean, like we did before. And I introduce you something you've never seen, it's gonna fail, right? Well, with a PD approach or an ODE, it doesn't. So while avoiding static or moving options. So for example, these are static things, but I'll show you video very soon. So this is the ground. Let's say I'm moving and there's an obstacle on the road. I want to avoid and go to this lane if there's no restriction, right? Or I want to turn and there's an obstacle, means I have to go and then turn, right? So same thing, there's a lot of scenario, I can do a lot of virtual, so I can do mixed reality, which you cannot do if it's just data-driven, right? Unless you do a lot of augmentation, retraining, but you don't have to. If you've learned the dynamics of what's a car, you can, with these methods, you don't have to learn everything. So, so these are other obstacles, in target reaching, this is another one where you can have different, basically trajectories based on your, on what's allowed. And, if there's other, cars, etc. All these are fine. So this I'm just showing you, a car is avoiding a scooter, right? So how would you do that if you didn't have a model, right? It's very hard to learn everything. And this is scooter. This is from data from like the car, for example, but the scooter I put it. And there's never seen a scooter, for example. Let me show you another one. Okay, so a car is avoiding instead of reaching a target. So this is the case, for example, is a target I just put on purpose the target there. So you see it modifies automatically, and of course the car is eventually going to go that direction. So the car is avoiding two scooters. It doesn't matter how many, I can put anything I want on the fly without learning, but I'm learning how a car moves, the basic movement, and then I learn to avoid by having interaction potentials. You see, in physics-based dynamic approach, you can put a lot of constraints, and depending on the driver, I can learn the dynamics of this driver or any driver, and I can say how courageous this driver, how close, what's the tolerance, or based on regulations, of course, from every country, etc. So all I'm saying is the sky's the limit now. I think we can do a lot of things, assuming, of course, we have the vision works and you can perceive and can track some points on the trajectory of vehicles. Let me show you another one. Okay, so this is, oops, stop playing. Okay, so I can get trajectories now of cars. This is bird's eye view real world. I don't know, it's not playing the whole thing as I wanted, but anyway, collision with virtual square. So here's the thing. Oh, let me see. Oh, no, I wanted to show you this one. So let's start this one. This is, okay, they are just moving, so I can track trajectories, right? I use networks that I showed you before, but there's other networks that can do 3D, 2D, but this is a 2D problem, it's not a 3D problem, because they're on Earth, right? 3D becomes if they're going up the hill, etc., but still it's on a plane, local planes. So if you do that, like, can you track, right? And the green is the ground truth, red is the prediction. We're predicting very well what's going on. Now, this one is a near miss because we care a lot about what happens, and there's a lot of data. So this is a virtual scooter, and here I'm predicting it's a near miss. They're not going to hit each other like in this case, but that's a collision here because you're predicting is going to collide, you see? So this is the advantage of using the approach I'm telling you. And I think I'm almost done here, but let me see. Okay, so how fast is this? This is very fast, right? 0.06 seconds basically per frame, which is very good. So predict 10 frames less than 4 seconds. And we have 16 agents and unexpected obstacles. We use RK4 to solve the ODEs existing software within a framework. And, it takes pretty good, but it's on 800 GPUs. Of course, we didn't optimize, right? I'm just telling you it's fast. Why it's fast? Because the ODE that doesn't have to make degrees of freedom, and I don't have to relearn, right? For every obstacle that can happen, right? So basically, what did we learn from this? Learning continuous temporal dynamics with agent interaction using ODE in latent space. We model agent-to-agent interactions based on distance and interaction intensity. Interaction is velocities. Of course, I use the stages, as I said, position velocities, but also interactions with others. Like we're not just model one car, right? It's the car in association with the other cars or pedestrians or whatever. So can deal without learning in case of obstacles, agents not in the trained data sets. That's the control approach. And we have coupled this dynamic data-driven approach with models. So the agent does dynamic change in the environment without learning based on change. That's as you all experiencing, that's why you want to augmentation, including us. Just data is not enough. You have to at some point do the science. So we've done extensive experimental study. We do better than others, but what can we do? Let me see here. I want to future while using this fusion approach, okay, of data plus ODEs plus control. So like we're trying to model prediction of near misses and other potential accidents. In Asbury Park, New Jersey, we're getting data of a real-time camera. And we propose trajectory modification to avoid near miss and accidents. And we integrate real-time sensor information. What we also do, there's a lot of expertise with facial tracking, etc. Okay, what is the driver doing? And, maybe going towards an accident, etc. At some point, as you know, the high-end German cars, which I like a lot, they are interconnected. Okay, they have this interconnectivity. Okay, Mercedes to Mercedes or BMW. But at some point, there's going to come a day where everything will be connected to everything. But that doesn't tell you what the driver is doing. So I don't want only to know what the car is doing, but what is the driver distracted? Unless you do the whole shebang, all these things, which we can. We have technology, just the integration is difficult. It takes time, but this is what we're after, right? To do a holistic approach to, because I have a real-time system to detect distractions, accidents, etc. for the driver. Now we have the cars, what they're doing, we need to couple them. And of course, this is amazing application, digital twins, airborne data, anything where we have dynamical systems coupled, which it is the reality, right? That's where we're after, and this is what our goal is to achieve, right? So, so anyway, thank you very much, and If you have any questions, please let me know.
Thank you, Dimitris.
Yeah.
Any questions for the speaker?
Sure. The mic is here. The mic is here.
Answer a question from there. Does it hear me?
You can try.
Okay. So hello. I just want to ask. Today it's a bit unclear for me. You said at some point that, well, I did not catch that part very well. You said that at some point that you do not like to use Kalman filters for some reason. And can you repeat again what were the reasons why you prefer something else? Maybe, I don't know, data driven or something else to Kalman filters?
No. I'm using a Kalman filter, not the traditional Kalman filter, but I'm using in a network. So I learn how to predict better than what a Kalman filter does, because a Kalman filter has assumptions. The noise has to be Gaussian. If you want to prove that your filter works, it's for simple linear systems and Gaussian noise.
Of course, but you can also linearize, even if it's non-linear. You can use, for example, the EKF or the UKF, and linearizes the system, and it works on also on the CPU. This is because this is also a little bit weird, because you use, for example, a 100 GPU with 40 gigabytes, and that. And here is also my second question, somehow tied. The first one: how much memory of that A100 do you use? Do you use all the 100 gigabytes?
We use 48 gigabytes GPUs at this point, but what percent per GPU I use? I don't use too much, because remember, I have few frames. So I think from what I know from my students, I think I use at least half of it, maybe.
Okay, so don't you think that the trade-off is a bit more? For example, you could make the prediction using the UKF on the CPU.
Let me tell you something. When you run it, it's very fast, right? When you train, it takes time, and you use a lot of memory. But when I remember that when I use the ODE, the system, I've already processed with the vision networks, and I get dots. That's very fast, right? I don't put images for the ODEs, right? I use points, tracked points. Like what the previous speaker said, like I'm analyzing using the previous method I described, like you know, whether it's LiDAR or these days could be visual data. Very fast I process it, and I get points for every car. But then the ODE is very fast. But the whole thing, if I use both, I mean the vision and the ODE, I'm saying it takes space, because you have to analyze images. But and the reason why it takes even a little bit more time is because I don't use one car at a time. I use as many cars from the bird's eye view. I want to see multiple cars. If there are two lanes, I need to see both, right? Yeah.
Thank you very much.
What is fast and I don't have to learn is if I introduce an obstacle. I just run it. I mean, I'm not retraining. No.
Thank you. Bye-bye.
Yeah.
So if there are any future questions, I suggest we take them in the chat. Let's thank Professor Dimitris again for his presentation. And
let me stop sharing. Okay. All right.
so thank you, Dimitris. And we'll be taking the coffee break now. So kind of
Okay.
go ahead with the schedule. Thank you. So we'll be back.
Thank you, Ravi.
So we should be back in. So let's start with our next speaker. We have Professor Yuxiong Wang. He is from the Department of Computer Science at the University of Illinois Urbana-Champaign, and he's affiliated with the National Center for Supercomputing Applications. He's received his PhD from CMU in robotics, and his interests lie in computer vision, machine learning, and in particular in focus on few-shot learning, meta-learning, open world learning, 3D vision, and streaming perception. He's been the recipient of various awards, including the Amazon Faculty Research Award, the ECTV Best Paper Honorable Mention Award, and the CVPR Best Paper Award finalist. The floor is yours.
Thank you, Ravi, for the introduction, and hello, everyone. It is my great pleasure to be here. Today, I will talk about bird's eye view BEV perception, an important topic on 3D deep learning for autonomous driving. I will focus on some of our recent work on unlocking the full potential of BEV perception through bridging sensors, domains, spaces, and times. As we know, BEV perception has recently emerged as an elegant solution to autonomous driving because it unifies diverse tasks into a joint coordinate system. BEV space, in its simplest form, refers to the XY ground plane. In terms of the features, BEV space takes the format of grids on the XY plane. In terms of the task, BEV space models every task on this XY plane, such as the map and motion prediction figures illustrated here. A series of work has demonstrated that object detection, segmentation, HD map generation, and motion forecasting can all be projected into the BEV space and predicted in the BEV space. However, when it comes to designing such a system, how to adapt BEV features to a wide spectrum of scenario remains a major challenge. The widely used framework is to first learn the BEV features by directly reusing the existing backbones for cameras or LiDARs, and then projecting them onto the BEV space with coordinate transformation. And then general purpose data or convolution heads are employed to handle different tasks. While such a pipeline is relatively straightforward and shows some initial potential, it is an oversimplification of autonomous driving scenarios, where a wide spectrum of tasks and heterogeneous sensory data have to be tackled to achieve optimal performance and ensure safety. To this end, our first key insight is to broaden the horizon of BEV perception across diverse sensors or modalities and domains. We explicitly leverage the complementary information from different modalities and improve generalization across domains, leading to more expressive, versatile, and robust BEV representation. Our second key insight is to broaden the horizon of BEV perception to support a wide spectrum task across time and space. Generally speaking, there are two types of tasks. The first type is object-level tasks, such as 3D multi-object tracking, MOT, which involves tracking moving objects that occupy a relatively small portion of the overall BEV feature. The second type is scene-level tasks, such as generating accurate high-definition maps, HD maps, where we need to cover a region spanning over 300 meters and digest information from extensive long videos to construct HD maps. Therefore, by exploring the learning and utility of BEV features in a wide range of scenarios, we aim to push the limit of BEV perception and unlock its full potential. Along this direction, our group has explored four important themes in autonomous driving. They will be the focus of today's talk. For learning BEV features, I will discuss how to encode multi-model information in the BEV features and how to adapt BEV features to different domains. On using the BEV features, I will present how to enable spatial-temporal modeling for both object-level 3D MOT and scene-level HD map construction. Okay, as a first step of any perception system, we need to learn expressive BEV representation. We achieve this by BEV Guide, a BEV-guided, comprehensive, and versatile multi-model fusion architecture. This is a joint work with my student Yunze and colleague Liang Yan. Our approach stems from recognizing that we are constantly immersed in multimodal environment in our daily lives, such as viewing music videos through our eyes and ears. Multimodality here provides us with a more complete and diverse experience. Similarly, in the context of autonomous driving, multimodality typically refers to the employment of a variety of sensors, such as camera, LiDAR, and radar, among others. The purpose of this is to fully apprehend the vehicle's surrounding environment, facilitating appropriate and responsive actions. So the key motivation behind our work is threefold. First, previous multimodal fusion studies often incorporate inflexible designs tailored to a limited and fixed set of sensors. Second, this prior effort don't dynamically adjust the weighting of different sensors in response to the ever-changing input samples. Finally, existing research frequently underestimate the distinctive capability of a radar sensor in enhancing the perception and prediction of environment. In light of these motivations, we would like our model to be able to take input from flexible sensor configuration, including but not limited to different combination of camera, LiDAR, and radar sensors. Given that different sensors are natively represented in different coordinate systems, we choose to bridge them within the BEV coordinate. This is for three important findings. First, almost everything we care about in the driving scenario stands and moves on the ground plane. Second, BEV simplifies 3D to 2D. And finally, BEV is an expressive and concise coordinate system. Previous fusion method fused different sensor features by projecting them into the unifying space. By contrast, our key insight is to query sensor features from the unifying BEV space. Doing so allows our model to decide the weights of different sensors and builds the representation bottom up from BEV. So our pipeline started from the flexible sensor pool and some sensor-specific encoders to extract the feature embeddings for each modality. Then a BEV-guided fusion model fuses the sensory features into the BEV coordinates. Finally, various downstream tasks can be addressed by using the BEV feature map. Notably, our BEV guide fusion model is a sensor-agnostic attention block, where queries are from BEV embeddings and keys and values are from sensory features. Camera, LiDAR, and radar each goes through the attention block in parallel, and we aggregate the BEV feature maps with concatenation. We encode the geometric correspondence as positional embeddings. For cameras, we use a camera projection equation to build the similarity between the image pixels and BEV positions, where positional embedding is represented by intrinsic and extrinsic matrix. Similar for LiDAR and radar, position embedding is represented using the transformation matrix S. Our method achieves superior performance in the segmentation task. As shown in this figure here, brighter regions means a higher chance of being vehicle on the BEV frame. Including multiple sensors efficiently improve the perception quality. Quantitatively, we observe leading performance in not only segmentation, but also detection and vehicle velocity estimation tasks. Notably, BEV guide can be used with different combination of sensors, and the using of them achieve the best result for all the tasks, as shown by the last rows of the table. Not surprisingly, we notice that LiDAR sensor is more important to segmentation and detection tasks, while the radar sensor plays a vital role in the velocity estimation task. A detailed analysis shows that the radar sensor helps improve the perception of a more distant object, which aligns well with its physical property. We also find that large multimodality reduces domain gaps and increases robustness under different weather and lighting conditions, such as from day to night or from sunny to rainy scenarios. However, in practice, the availability of modalities may vary across different domains. This leads to an important and natural practical question. How can we facilitate knowledge transfer across different domains and across different modalities in the context of BEV perception? In our due cross work, we investigate this question. This is also the joint work with my student Yunzi and colleague Yang. More specifically, when dealing with adaptation, previous masters often assume two scenarios. One scenario is cross-modality, where training data are captured in a different domain from the testing data. For example, day and night, light and dark, city in country A and city in country B. But the input of sensor modalities are the same across the training and testing phases. The second scenario is cross-modality, where testing data have a different and often fewer type of sensory modality available than the training data, but they assume the same data domains. However, as mentioned earlier, a more realistic setting is the simultaneous domain gap and the modality gap between the training and testing phases. Here, we consider the camera and LiDAR modality being available during training, and only camera is available during testing. Under this scenario, we find that, surprisingly, using the additional modality as a direct supervision, that is taking LiDAR as that depth supervision, in fact leads to worse result than not using it or as shown in the table. To account for this challenge, we propose a knowledge distillation strategy to transfer the LiDAR knowledge in the training phase to the camera model in the testing phase. So our do cross includes three components. First, LiDAR teacher uses voxelized LiDAR point clouds to transform image features to the BEV frame. It provides essential knowledge on how to guide image learning given LiDAR information. Second, camera student is supervised by the teacher model as well as a LiDAR ground truth. In addition, discriminators are used to align features from source and target domains. Here we show a day-to-night adaptation scenario where we compare do cross with a direct LiDAR supervision and adversary learning model. Our model leads to more stable and consistent segmentation results. Do cross achieves the best BEV segmentation performance in adaptation settings compared with the classic domain adaptation and the depth supervised adaptation method. Superior performance is also observed for the segmentation task under various domain shift scenarios, including day to night, dry to rain, Boston to Singapore, and a nuisance dataset to lift dataset. In addition to the segmentation task, do cross achieves the leading result on the detection task under both modality and domain shifts, as shown by the left table. Do cross also benefits from more powerful encoder backbone, as shown by the right table. Here we show that all our components contribute to the final performance. Note that, as discussed earlier, direct LiDAR supervision without knowledge distillation leads to worse result. This is due to the increased domain gap introduced by directly using source domain LiDAR modality. So far, we have discussed how to learn comprehensive, versatile, and robust BEV features. After learning such BEV features, it is still unclear how BEV features support autonomous driving tasks. Specifically, the features located on fixed grids. How could they decode the object on each position and model constantly dynamic traffic situations? Our PFAP track offers an end-to-end framework that enables these properties in the context of 3D multiple object tracking MOT tasks. This is a joint work with my students and our collaborators, Jie, Pavel, Dan, and Sergey. As a crucial task in autonomous driving, 3D MOT aims to coherently estimate the positions and the identity of objects from the images captured by the surrounding cameras, which is the 6 cameras in nuisance, for example. In this video, we show the results predicted by our PF track. An object is supposed to have a coherent color over time. And we can see that in the video, our prediction is quite smooth. Compared with the previous method, our PF track has made significant improvement in several aspects. First, PF track generally improves the association ability of 3D MOT approaches. In MOT studies, ID switches are typically used to evaluate the association ability of trackers, where one ID switch indicates wrong association. So lower is better. As in the comparison, PF track has more than 90% less ID switches compared with the previous state of art. This means an order of magnitude fewer errors. Second, PF track delivers a simple yet effective approach to robustly address handovers and occlusions. For example, the first row of these images show a vehicle approaching and switching from the front camera to the front left camera. Even in this challenging scenario, our framework simulates output of high-quality 3D bounding boxes across both of the cameras. This is an example of camera handovers. For the bottom 2 rows, we illustrate 2 examples of handling occlusions. As we can see, even if an object is occluded, our framework tries to maintain 3D positions and associate it without explicit re-identification. So what leads to the effectiveness of our PF track? The key is to conduct some kind of spatial-temporal modeling for both past information and future movements. More concretely, as illustrated here, a pedestrian appears on the front right camera on T0. Our tracker tracks it for a while, where it switches to the back right camera on T1. However, on T2, the pedestrian is occluded by a very large truck. During this difficult time, our tracker manages to keep the state of the pedestrian. Eventually, the pedestrian reappears and the PF track correctly reassociates the pedestrian. Our past reasoning highlights using historical information to refine the bounding boxes. As we all know, detecting 3D bounding boxes can benefit multi-view information. As in this example, the bounding box for the pedestrian is drifted in the beginning, T0. However, when we combine more information at T1, the quality of the bounding box improves. This is how we propose past reasoning to improve the quality of the tracker. As for future reasoning, it emphasizes the importance of preparing for the future movements of object. Again, as in this example, our tracker can predict future trajectory in T1. In this way, even if the pedestrian is occluded in future frames, T2, we can still maintain a relatively accurate state with the motion prediction. After the pedestrian reappears, our tracker decodes its latest position from the maintained states. Therefore, our framework avoids an ID switch caused by occlusion. The last part of the framework is how we can seamlessly handle the switches across cameras and address occlusions without explicit re-identification. The key insight is to build a query-centric end-to-end framework. In the framework, we represent each object as a query and iteratively decode its bounding box on every frame. So I would like to further explain the intuition of decoding the queries from the surrounding cameras. Here, the center vehicle is our ego vehicle. The yellow circles are the queries of the object on BEV. When we try to decode the queries, we compute the cross-attention between the queries and all the images. Notably, the cross-attention is guided by the camera projection so that each query focuses more on the image region that are coherent with its 3D positions. In this way, we can generate 3D bounding boxes across images and frames in an end-to-end manner. Here, I would like to highlight two important properties of our PF track empirically. First, as mentioned before, PF track has significant advantages over the previous state of art, especially in its ability for accurate association. Second, we project the trajectories and bounding boxes predicted by PF track onto the BEV. Notice that the point clouds here are only for visualization, and they are not the input of the PF track. Notably, PF track, though only uses images, generate coherent tracking results in 3D and captures the motion patterns of objects. We also conduct ablation studies on PF track, especially the past and future reasoning models, beginning from the baseline that uses queries to end-to-end track objects, and in past reasoning and future reasoning can significantly improve the performance. As our system is end-to-end, the two modules are more beneficial when used jointly. In addition to addressing object-level tasks, we also pay attention to a timely problem of off-board HD map generation. HD maps are essential infrastructure in self-driving, but they are previously annotated by humans and thus too expensive to be scalable. Therefore, we aim to extend BEV perception to this task. And our goal is to solve two problems. First, BEV features captured from different locations and time steps contain different views of the scene. How to make them complementary to the final prediction. Second, off-board HD map generation has to process a large amount of data, virtually unlimited number of data, such as thousands of frames, right? Previous BEV perception only addresses online tasks. It's an important step to generalize BEV perception to off-board scenarios. Our recent MOE map addresses these two problems, and this is a joint work with my students in Anchorage. Imagine we have collected a sequence of images and want to infer the surrounding map so that we can avoid violating traffic rules and make informed plans while navigating. The HD maps are the lines, crossings, and boundaries as visualized here. Because of its importance, various approaches have been developed, as exemplified by the recent BEV perception algorithm, which use the computation on board the vehicle to predict HD maps. So, however, if you look at the visuals here, these methods suffer from the inconsistent result captured from different viewpoints. For example, the heavy urban traffic has frequent occlusions, and they can block the observations and make the prediction fluctuate a lot. As HD maps are static structure on the road, such predictions are not reliable enough for the safety-critical autonomous vehicles. On the contrary, the common industry solution is to treat HD map construction as an offline task in data centers. A considerable number of human annotators are hired to manually label the input sensor observations and generate high-quality HD map. Clearly, such an approach is costly and not scalable. Second, Since the road status is constantly changing, human labeling struggles to keep updated with these changes. To this end, we propose and started the task of off-board HD map generation. Our objective is to automatically generate the high-quality HD maps as shown in the visualization. Meanwhile, significantly decrease the human labor required in this process. The first challenge is how to be scalable to a large amount of the data. Well, in general, more data could lead to better performance. Each sequence or video clip may contain thousands of images covering a few hundred meters. Therefore, we need to design an algorithm that can reason and combine such a large amount of data into a unified HD map. The second challenge is how to automatically select the reliable sensor input for HD map generation so that the results are multi-view consistent. As in this example, ideally, we would like an algorithm that relies more on frame N as it has no occlusions compared with the frames 1 to I, which have occlusions. To address such a challenge, right, and to deal with a very large number of frames, we propose region-central fusion. So it separates each region on the HD maps and then aggregate all the onboard prediction on this region. In this process, our MOE map framework predicts a confidence score for the regions of each frame and uses a weighted average to combine them as a final result. In this way, our final result fuses the best of each individual frame and generates a high quality, high fidelity HD map. So the aggregation of BEV features plays a vital role here. And we illustrate that combining BEV features is effective for generating multi-view consistent maps. So to highlight the regions with a larger fidelity, we propose to further augment multi-view consistency with the unified 3D structures of the entire scene, right? With NeRF being a well-established 3D reconstruction approach, we reconstruct the 3D geometry of HD maps with a voxel NeRF. Then we learn the confidence score of each region with NeRF providing auxiliary inputs. Intuitively, we hope the voxels closer to the NeRF surface have larger weights. As visualized in the figure, our voxel NeRF produces a high-quality 3D reconstruction with clean lanes, boundaries, and pedestrian crossings. So the overall framework of our MOE map integrates these key designs and components. First, our framework digests the sensor observation with an onboard model, such as regular BEV perception models. So we obtain BEV features F and HD map semantic S. And here we can use any BEV perception model. Then we train a voxel NeRF from the whole video sequence and provide it as an augmentation for multi-view consistency. Finally, an uncertainty network predicts the confidence score for each region of every frame, as shown in the green square. The predicted confidence weight the BEV features on every frame, and we fuse them into a multi-view consistent HD map. As the most important aspect of the off-board method, our MOE map benefits from more frames. This figure shows that how the MIOU of HD map change with respect to the frame numbers. The blue curves are our MOE map. The rest two are baselines. So as clearly shown, MOE map has significant improvement with more frames and is better than the baselines. This is critical for off-board method, as the scalability to a large amount of data is essential. This video further intuitively shows the refinement mechanism of MOE map. With more and more data, our approach gradually refines HD map predictions with the incoming observations. We compare our method with previous HD map generation algorithm. Compared with previous online algorithms such as HD MapDAT and simple BEV, our approach of fusing BEV features is beneficial, even with a fusion strategy that is as naive as computing the average features. So this validates the effectiveness of off-board fusion. By leveraging our adaptive fusion strategy introducing MOE-MAP, we enhance the contribution of BEV features from regions of high confidence and significantly improve the performance and the fidelity of the HD maps. So in conclusion, under the unified BEV coordinate, our work learns representation from multiple modalities and domains and empowers diverse tasks across space and time. Therefore, significantly broaden the horizon of BEV perception. So for BEV feature learning, we propose BEV Guide, a comprehensive and versatile multi-model fusion architecture, which benefits from a diverse set of sensors and performs various driving tasks. We propose DoCross, a robust knowledge distillation model that works in cross-domain and cross-modality settings. Also, for downstream tasks, we propose PF-Track, a 3D MOT framework with minimal ID switches by modeling how queries are changing in the past and the future. We also introduce MOE-MAP, the first off-board HD map generation framework that fuses BEV features with respect to their consistency with the global 3D structure. Thank you for your attention, and now I will take more questions.
Thank you, Yuxiong. We have time for 1 or 2 questions.
Can you give us more details about, let's say, technical details, how you implemented this solution? Is this, let's say, programming languages, frameworks, and running time?
I didn't hear it clearly. Can you?
Okay, so can you give us a bit more technical details? For example, what programming languages did you use to develop your solution? What frameworks, and the overall running time of your solution? And also the resource consumption would be interesting.
Okay, so again, so these are developed under the standard, right? So this kind of a framework from building upon the public resources. So for the first 3 works, right? So the BEV Guide, the DoCross, and the PF-Track. So they are kind of, we're trying to make it lightweight. For example, for the BEV Guide, when we're trying to fuse the different modality, different sensor, right? This is a general framework. Again, that's a general fusion framework. We hope we can benefit from, let's say, more powerful architecture. So this is also what I showed in the presentation. But we showed some kind of actually a very lightweight design, let's say the cross attention actually improve the performance. For the last piece off board, so we're trying to relax the restriction from the computation because we are trying to introduce this off board setting, right? Assuming we have kind of the a lot of data, we have relatively more compute. But all this works, I would say we don't consume a lot of computing resources. This is a standard compute in academia. The PF-Track is the collaboration when the student is doing internship as TRI. So that involves some kind of compute, but generally I would say, and all these are kind of open resources, so you can check the detail.
Okay.
Thank you.
So in the interest of time, I suggest we discuss the questions offline. So let's thank the speaker again.
Thanks, everyone.
Thanks, Yuxiong. So in the next talk, we have Songyou Peng. Are you there, Songyou?
Yes. Hi everyone. Can you hear me? Can you see me?
Yep, definitely.
Awesome.
Just give me a second. You should be able to share your screen.
I will try now.
Yep.
Oh, cool.
So in the meantime, I'm going to introduce you. So Songyou Peng is currently a final year PhD candidate at ETH Zurich and the Max Planck Institute for Intelligent Systems. He's supervised by Mark Polyface and Andreas Geiger, and his research focuses on 3D vision and deep learning. Songyou has gained experience as a research intern in Google Research, Meta, Reality Labs, Research, TUM, and INRIA. Its primary research interests include both neural implicit and explicit representations for various applications, such as 3D reconstruction, and novel view synthesis, SLAM, and 3D scene understanding. So the floor is yours.
Thanks so much. Hi, can you see my screen?
Yep.
Cool. Awesome. Hi, everyone. Thanks a lot for Ravi's warm introduction, and thanks for inviting me to give a talk in the workshop. And yeah, so like, to be honest first, I'm not really in the field of autonomous driving or this, but I'd like to share some of my thoughts on like 3D deep learning, and also like recently like the hot topic in like NeRF and CLIP, and how can we really use this kind of information to advance the 3D reconstruction, the understanding tasks. Yeah. But I will like try to make the talk as easily accessible as possible, so everyone will still understand, even it's not really about like outdoor or autonomous driving. So yeah, first I'm a fourth year PhD student. I'm like final year, basically. I'm graduating this fall, and so if you are having any interested opportunities, and please reach out as well. And also, yeah, during my PhD, I did two internships, one at Meta Research, Reality Labs, and also Google Research. So yeah, my PhD topic is mainly about like how to apply neural scene representation for 3D reconstruction and like scene understanding. Yeah, I have like author and co-author like bunch of papers within this domain, and like due to the time limit, I will only focus on like two recent papers from me. Basically, the focus is exactly as this talk about like how do NeRF and CLIP advance this 3D reconstruction and the understanding with like paper from last year CVPR and this year CVPR. So okay, if we decompose this the title of the talk, we will have basically it's like two different directions. So how does NeRF advance the 3D scene reconstruction, and how does CLIP advance 3D scene understanding? And I will start from the first one. So yeah, so I don't know, like probably many people in the audience already pretty familiar with NeRF. Like it came out at like ECC 2020, and there is and it gets like so popular nowadays because of its stunning and novel synthesis results. Even they can capture such a those like really shining surfaces. However, there are still some existing problems. For example, even though the rendering itself is quite nice, the underlying geometry of NeRF is actually pretty poor. That has been proved or shown in a bunch of papers. And what's even more important, or like the essential issues, is that like they always assume having the ground truth camera poses given, right? So like then like we are wondering, like, is it possible to somehow solve these two issues? So what about like giving RGB and depth sequences? We can on the fly learn the 3D scene representation that has the appearance, geometry, or dense geometry, as well as the these camera poses all at the same time in an end-to-end manner, right? So this comes to our very first paper, like this a paper from last year CVPR called Nice Slam, neural implicit scalable encoding for SLAM. Yeah, it's a joint work with like very talented students. Zihan, like he was still even a undergrad student at that time, and also a bunch of other people from Zhejiang University and the ETH. So yeah, so like we are not really the first one during this. Well, someone's okay. So yeah, so we are not the first one. We were inspired by this paper called IMAP. That was basically the very first neural implicit based online SLAM system, which they can you can see like they do exactly this task, like jointly optimize camera poses and the dense geometry all together. And however, like this method has a bunch of issues due to their use of single MLP. For example, like when we apply these to a larger scenes like this, they actually will fail after a while due to the capacity limits. And then also like every time you input a new frame, then I will update the entire MLP, then it leads to the catastrophic forgetting problem. And also, yeah, since you also need to update the entire network, the slow convergence was obtained. So in NiceLam, we actually propose a very simple change, which is having a bunch of feature grades at different resolution, plus some tiny MLP that is pre-trained before, which allows us to be applicable to larger scale scenes and also allow local updates so we don't suffer from any forgetting problem. Also guarantee much faster convergence. And how do we achieve that? So again, like so given this RGBD sequence as input, the goal is to update basically the mapping part is our hierarchical feature grid, and also the tracking part is the camera poses for each frame, right? So how do we update them on the fly? So what we do is that like, so, okay, we randomly sample rays on the current frame, right? And then we shoot the ray, and then we sample along the ray. Then we can extract for each point along the ray that we sample. We can extract with trilinear interpolation to extract the features from different feature grades. And once we get this feature, we can input those features into different levels of small MLPs to obtain the corresponding, like for example, cost level occupancy and also fine level occupancy, as well as the color prediction. And then like with a NeRF-like volume rendering equation, yeah, like this whole process can be used to generate the corresponding depth and the RGB images. And once we have that, we can simply calculate the reconstruction loss between the input depth and RGB with our generated modalities. So since this whole pipeline is differentiable, our like rendering is differentiable, so we can minimize this reconstruction loss to alternatively update this hierarchical feature grid as our mapping step, and also the camera poses as the tracking. So like the whole pipeline is like very simple, and here we show some results. So even on these like very small scenes on ScanNet, like so we compare to our re-implementation of IMAP, and we can see that like we can already obtain much cleaner reconstruction, also like better reconstruction on or better tracking performance. And then even like when we when it comes to the ScanNet, the real world data sets, indoor data sets, and we can still obtain much better results, even though the input RGBD sequence are very noisy. And yeah. And also like, so on this scenario, basically we also compared the computation as well as the mapping and tracking time, and we are actually much better in every sense compared to IMAP, which is like another benefit of our neural scene representation. So yeah, that was a quick introduction to this paper. If you're interested, like you can check out our paper and code. However, like basically this paper was nice online in places SLAM system for only the indoor scenes. And what's interesting is that this hierarchical kind of feature grades plus tiny MLP seems to be a trend. Like basically one month after our paper, like this, like another paper, Instant NGP, came out as well. And then also they were doing similar kind of stuff like the hierarchical feature grade plus tiny MLP, and it was very interesting to see. And then like now after a year, then so many paper has been built on top of these kind of things. Yeah. Oh, here's something. Do you have questions or?
No.
Oh, okay, sure. No, but yeah, there are a bunch of limitations because it was like one of the first work in this direction. Like for example, like we require depth as input, which is a super strong cues for checking that we realized that. And after we want to remove this, and also like we are only limited to bounded scenes, so no outdoor scenarios is possible. So it's very interesting to see how can we apply similar kind of approach, but for larger scale scenes, like outdoor scenes or like outdoor data sets as well. And also, yeah, it's still not really real time. But then for these very first limitations, we actually have a follow-up paper coming out like from on archive, and basically it's called nicer SLAM, and the R represents for RGB only SLAM, so we don't need depth anymore. And what's interesting to see is that like even without the depth as input, our reconstruction can be like almost the same as before. Yeah, compared to other monocular kind of SLAM method, for example, like dry SLAM, and the reconstruction is much better. And even compared to our nice SLAM, it's actually giving you like even smoother results. And yeah, pretty faithfully reconstruct the scene that we have here. Okay. I hope this makes sense to you. Okay, and then like so once we have the 3D reconstruction from a scene, for example, these like indoor scenes here, right? Then let's say from nice SLAM or nicer SLAM or any other kind of 3D reconstruction method. Once you have this like kind of 3D geometry, what people will do is that, well, we want to do some high level scene understanding tasks. For example, very typical one is semantic segmentation. So given a bunch of, let's say like 20 classes of different objects like walls, floor, or cabinet beds or something like that, they are trained on those annotated data, but they are only able to also only test on those few common classes as well. So for example, now if you ask, oh, where's TV? Then this method won't work because they did not, the network was not trained for this, right? So this like, basically that's something like I'm especially interested on. So basically like, so there are so many other kind of 3D scene understanding tasks like affordance prediction, material identification, like real object retrieval, activity predictions, etc. All of those, like most of data sets nowadays, they don't have any data or like label annotations for that, right? Like, well, so, but still we are very interested in these. So can we have a system basically to do everything in one go, like have a system for all of these tasks? So like this basic come to the second project that I want to discuss is OpenScene. That is my Google project, Google internship project, and together with a bunch of amazing collaborators from Google Research and also Waymo. And yeah, so this paper is basically about like how can we do 3D scene understanding with open vocabularies. And yeah, we will present this in CVPR in like 2 weeks. And so the key idea for this paper is to try to co-embed like 3D features in 3D, like the features in 3D with the CLIP features. And like in terms of CLIP, the CLIP is basically a contrastive language image pre-training, right? So basically they can, they have a huge data set that is basically for each 2D image, they have this like corresponding like captions. And then they try to pre-train those two, like the text encoder and the image encoder, and try to have their the embeddings on the same space. So basically the image and text are already in the, they are already co-embedded. So our goal is try to do the following. So for example, now we have a 3D scene, right? So we can extract every single point in the scene, one feature vector, for example, like one vector here and the other one near to the window, right? And the goal is that like, is it we try to co-embed those feature vector onto the clip text feature space and via some 2D images, basically. And if we can already co-embed the text and image and the 3D in the same space, so we can utilize the property in clip. Basically, so for example, if you type in sit, it's the feature is lying very similar to or close to the sofa in the clip embedding space. So you can utilize this for a bunch of 3D scene understanding tasks. And how exactly we can learn such a text image 3D co-embeddings? And yeah, here I will introduce. So the idea is extremely simple, straightforward. What we do is basically like we have a 3D geometry given, assume it's given already, and then we also assume that we have a bunch of post RGB images that we can find the corresponding 2D points in those RGB images to the 3D points, right? So like this sofa points on 3D, we can find, for example, now 3 images corresponding to this point. And then what we do is we can use a pre-trained fixed clip-based semantic segmentation model, for example, OpenSeg or LSeg or like the recent OVSeg kind of paper to extract per pixel features. And then we can then extract from every corresponding images, we can extract the 2D features out. Then we can fuse them to the 3D, basically with weighted average. Very simple. And then what's next is that like, so we want to also train a 3D Minkowski net to encode the entire point clouds as input. And then the reason why is to get the utilize basically the CNN to incorporate the entire how do I say this, the receptive field of the entire room to help remove the noise that we introduce into the features. And then, however, this step, we call it a 3D distillation, meaning that we can utilize the 2D features or the 2D fused features that we mentioned in step 1 as the simple cosine similarity loss to reproduce. Basically, like for every 3D point, we can produce the point feature, and then want it to be as close as possible to the 2D features we produce, but without the noise in it. And in the end, like once this 3D network is trained, right? So we can actually simply use, so we have like 2 sets of features for each 3D points. One is the multi-view fused feature, one is the 3D features from our 3D CNN. And what we can do is like, we can do a kind of 2D, 3D ensembling to obtain the best final feature for each features on the 3D space. So once we have those 3D features, we can use it already, as I mentioned, for a bunch of 3D scene understand tasks, because now the features is on co-embedded with text and image on the clip space. And yeah, I won't go into details of this ensemble, but I will show some results and applications enabled by our OpenScene. For example, the very first one is open vocabulary, zero-shot 3D semantic segmentation. And here we actually did some experiments on new scenes. For example, here, this is the input LiDAR point cloud, right? And yeah, and like, so if you just simply fully supervise and train a Minkowski net on this bunch of classes, and that's the result. And you can see that you can actually reproduce the ground truth labels very faithfully. However, like compared to, so this on the bottom left is our method, OpenScene, the prediction results. As you can see, well, for example, on those area supposed to be the sidewalk, we are actually not as accurate as the ground truth prediction. Like actually in general, we are doing quite okay, but like not as accurate as enough as the fully supervised method. However, what's very interesting here is that, like, for example, in the supervision signal, this truck, the entire truck is segmented as a truck. However, our method will predict the back of the truck as trailer, which is actually even more accurate than the annotation. And that's actually super interesting because like we will realize that like our method is able to figure out, oh, some of the better annotations compared to even the ground truth data set. And then like, yeah, we can also, of course, do some indoor scene reconstruction, indoor scene understanding as well. So for example, now we are inputting this 3D huge house from Metapod 3D, which is probably like from some rich people's house. So like I don't know, 20 rooms, like 2-3 floors, etc. And then like, so again, we can do our 3D semantic segmentation on the 20 classes. And like, yeah, we can do decent jobs as you already know before. However, what actually make our method shine is that like we use the same set of features, these 2D, 3D ensemble features that we got. And we can actually also apply to like 160 classes, even like, so include many of those like tail classes. And what's interesting to mention is here, for example, here we are able to find or identify like a pool table, which was basically was segmented as a table before. So that's actually very interesting. Again, like we are able to find those like tail classes as well. So here, this graph can clearly show this the performance even more clear. So what's this graph is showing is that like, so we rank based on the number of instances in the training data set, the performance of our methods. So on the like the top 20 classes, like the fully supervised method significantly outperform our methods, our like zero shot method. However, like all the remaining classes or like remaining the tail classes, and you can tell that like our method is able to really outperform the fully supervised method because we are not really subject to the limited number of training data. And yes, and there's a application study as well that to show that basically our ensemble resource is actually very, or ensemble strategy is actually very useful, like much better than like the 2D feature or 3D features alone. And then like there's another application we show is that like, well, is it possible to query not from the text, like text query, but from images? What does it mean is that, so again, given some 3D geometry of an indoor scene, and then we can like search a bunch of images from internet. Let's say here we have an image of a dining table, a pool table, and also a sofa, for example. And then we can input those features into the clip image encoder, and then we extract the corresponding features. And then we can again do the cosine similarity check. And then we can actually detect basically the corresponding objects, which is similar to these internet images. And they are not actually one-to-one mapping, right? But still, like you can see that like, well, we can do a pretty decent job to find like the corresponding objects, even just with images. And finally, yeah, so we also develop a like interactive demo for like open vocabulary 3D scene exploration. And what does it mean? Is that like, so again, like having this 3D room, so we can type any kind of text query as you want. For example, we can like work on different kind of like common objects, like what I just already showed, like floor or bed. Then you can like highlight them in like, so in green or not green, yellow, green, or blue. The yellow means the highest similarity scores. And what's really interesting is that they can actually handle, for example, like Snoopy. You can find, oh, there's a Snoopy in the scene, and such a very big, like real classes. And also you can handle like those activities, or where can we sit? Like, yeah, you can highlight all those different areas where you can sit. And also you can type like glass, and you can see the window and the those shelf has the windows. Yes, and fragile, basically the properties. You can see a bunch of like doors. They are actually pretty fragile, right? Which makes sense. And also, oh yeah, so like activity, like cooking, where can you cook? Like you can highlight also the stove and the microwave. And also like we can handle like room type, like bathroom. Oh, where's the bathroom? So you can see, this area is like bathroom. And the last case is like abstract concept, like even those, what is festive? Festive is like a very abstract concept. And apparently like all those Christmas trees are highlighted in the scene. And I did not know before that, oh, there are actually like 5 or 6 Christmas trees in this family. Again, well, it's a very impressive. Yeah, and that's yeah, about the OpenSing. And basically in OpenSing we enable a bunch of new applications by these open vocabulary queries, and this we hope that like can influence how the researchers train the future 3D scene understanding systems. And like the real-time demo actually showed the possibility to directly apply to the AR, VR applications. And also like this idea is so natural to be applied to the autonomous driving setting, because I think if it's very interesting if like basically the people can type in wherever they want, what they care, and then during the driving will help the driving process will be much safer than before. Yeah, that's actually something I'm very excited to see in the near future. And I know that like a bunch of companies, from like big companies to small companies, they are actually already developing stuff like in these directions. And I'm very excited about this. And yeah, so that's basically it. I hope I did not run over time. So that's like 2 papers I introduced today, and I'm very willing to take any questions. Thank you.
Thanks, Songyou. Are there any questions for the speaker?
Yeah,
No
my few. Oh, sorry.
No questions here, I guess.
Yeah, I guess like the maybe it's a little bit away from the driving community.
Well,
Yeah.
in fact, today morning, the first talk was LidarCLIP, which was combining point cloud embeddings with image embeddings. So, no, it is in fact very interesting for us. And
Yeah, I think OpenSing is like definitely like close to this direction. Yeah. Cool.
So maybe like a really quick question here. So I was wondering if the depth information got sparse, because one of the key constraints in point clouds is that we don't have a complete dense depth representation like you have shown here. And we work on point clouds, on LiDAR point clouds. So would the sparsity change anything fundamentally in the way the 2D, 3D feature extraction?
Yeah. Cool. Yeah, it's a very interesting questions. Yes, basically, well, I think one issue of like the point cloud compared to the indoor scenarios I was talking about is actually that how we actually even get the 2D fused feature from the multi-view images, because you cannot really do the multi-view, or how do you say, you cannot really do the visibility check because the depth information is so sparse, right? As you said, so you cannot really know whether this point is really visible on another image
Yep.
or not, right? So that's actually an issue. And however, like, so that's basically what we do in the new scene experiment is that like we can actually just simply use all images that is seeing this current point and just like simply get the and do the weighted average for this to get a feature, and then use that features to be the supervision signal for our 3D distillation network. And we realized that actually our student basically is our 3D CNN that we learn can significantly outperform even the supervision signal we have, and which is interesting because like, well, 3D CNN can take all the informations from the entire point cloud from like 0.5 seconds of all the points and then make the prediction. And this actually guarantee you a much more consistent features compared to just like the 2D fused features. But then like we learn only from those 2D features. And that's like the very interesting thing. Yeah.
Merci.
Cool.
Thank you.
I have a
Thanks.
quick follow-up question if we have time.
Yep.
Perfect. So thanks for the presentation and the very interesting works.
Thanks.
I have a question. If we take this to the autonomous driving setting, maybe especially like high-speed driving, do you think we would be like severely limited by the sparsity of the views? Like with the views, we'll have so many fewer images per square meter or whatever if we're driving, say, 100 kilometers per hour. Do you think we'd have to adapt these methods to work with that, or is it not a problem?
That's a very interesting point. Yeah. So like, I think this won't be an issue because like even now, for example, now what we do is that we only use the very last timestamp during the training. Basically, the feature we use for supervision is only basically each 0.5 second point cloud, which has like, I don't know, 200,000 points or 300,000 points, but we only use the last the points from the very last timestamp has like, I don't know, 50,000 points, and use those kind of features as the supervision signal. And that's actually not too dense in my opinion, right? And then it can also still works pretty well on that scenario. But like, for example, for very high speed kind of scenario, I don't know like whether it will work or not. Probably we need some like adaptation for that, because yeah, definitely like the different speed will make a huge difference, right? And yeah, like, so I don't know whether it will work out of box, but definitely with some adaptation you can, I hope it will work well. Yeah.
Okay,
Thanks. Awesome. I guess I can stop, right?
Yep, let's thank the speaker again, and
thanks a lot.
let's move on to the next speaker. So Apoorv, can you share your screen?
Unmute myself.
So it's loading. Yep. So just a quick introduction. This is the second accepted paper in the workshop, and this is Vision Radar Fusion for Robotics BEV Detection, a survey by Apoorv Singh. Go ahead, Apoorv.
Sorry, it is a little lagging. Yeah, let's get started. So hi everyone, I'm Apoorv, and I have an accepted paper in this workshop. It's called Vision Radar Fusion for Robotics BEV Detection. It's a survey paper. And yeah, so I'm a tech lead at Motional. If you don't know Motional, we are the same company who developed Nucine's dataset, but right now we have rebranded ourselves and currently we are known as motion. And before I get started, let me go ahead with a quick video to show what we do.
Where would you go?
Your car has arrived.
What would you do? With more freedom to get where you need to be.
Video still lagging. I'll just skip the video. But yeah, I'll just go through the slides instead. So, so we are doing level 4 autonomy, and currently these are the list of cities that we are working on: Vegas, Pittsburgh, Boston, Los Angeles, Singapore. And yeah, so currently we have our L4 autonomous car already deployed in Vegas and Los Angeles through Lyft and Uber platform. And right now we are also looking at increasing the ODD of ours and also having more drivable autonomous driving capabilities on those regions. And this on the bottom right is one of the snapshot from our Vegas facility with all the autonomous cars. And this platform is Hyundai's Ioniq 5. It's a full electric vehicle. And we have partnered up with Hyundai to develop this platform. And so let's go with the sensor stack that we have. So it's going to come in a second. So we have in total 30 sensors in our cars, and out of which 13 are cameras. So here we are representing some of the sensors here. So out of 13 sensors, we have 8 medium field of view cameras in which we primarily do the detections. And then we have a 1 narrow field of view camera through which we do the traffic light detection, because we need a narrow field of view to detect the state of the traffic light. And we have 4 wide field of view cameras to detect any close range objects that we might miss with narrow field, with medium field of view cameras. And I'll share this. I'm unsure if this video will show up, but this is the current performance of our perception stack in the Vegas city. So this data set might look very similar to new scenes, but it is more complex than that. Like, to give you an example, at every particular time step, we see around 300 objects on our scene. And yeah, if you're familiar with Vegas, this is one of the Vegas prime strip street that we have. But yeah, I'll skip ahead this slide. And yeah, so I'll go ahead with the motivation why we came up with this paper was, so as you know, like in autonomous driving, LiDAR is the primary sensor, but we are also trying to develop a redundant detection algorithm which can work in place of LiDAR. And the redundant detection algorithm is based on camera and radar. And so this plot theoretically shows that we can achieve everything using just camera and radar and even more. But these are theoretical ways. But we, we are yet to beat we are yet to beat LiDAR just using cameras and radars. But so this, our team has published few papers in this line. So I'll be talking through that. And the survey paper talks about the whole whole literature around this topic as well. So there are, like, if I have to be very simple about the implementations, it can be divided into 3 parts: early, late, and deep fusion. Early fusion is kind of still an unsolved problem, and most of the research is happening around deep fusion. And late fusion is, I guess, one of the most accepted way to fuse cameras and radars through the past, and also like a couple of other keynote speakers also spoke about it. It's based off SORT algorithm, which uses Kalman filter and Hungarian matching algorithm. But most of our current research is based on deep fusion to get better detections using camera and radar features. So this is one slide on late fusion, and I won't go into too much detail. I'm sure you all are very familiar about that. So we use camera as well as radars for detection, and then we use cost matching using Hungarian matching, and then we predict future using Kalman filter. And one of the problem with this approach is it is late fusion, and we can easily have a lot of false positives because there's no interaction between the encoders of camera and radar. So our primary research is on the deep fusion. This is one of the paper that we are currently working on. So I'm allowed to share it. We have a patent filed on this. So this paper is based off data 3D style architecture, And if you don't know what Data 3D is, I'm sure you have heard of what Data is. It's from Facebook, and they have CNN-based backbone and transformer-based detection head. And so let me go through this image. If my pointer works in real time, here on these two green blocks, we see camera-based backbone and radar-based backbone. And you can interpret that as any simple CNN-based backbone for cameras. And for radar, it's a fully connected layer, which encodes every single radar point, which is represented by four numbers, essentially. And then we encode those 4 numbers into a 256-dimension latent space to extract the radar features. And then this big block in the gray color, this is our detection head, which is the major novelty of this approach. So we start off with initial queries, which are in bird's eye view, and then we run it iteratively through our transformer-based decoder to fine-tune those initial queries so that they can be transformed into final bounding boxes in the bird's eye view. And the way we do this single sequential decoder is through this. I'll just go through that, and then we do it 6 times. So first we get our initial queries, and then we map the query to a 3D point in the bird's eye view. And then we extract multi-level image features through our CNN or transformer-based encoder. And then in parallel, because we already know what a 3D point this 3D query is representing, then we find out the top k nearest radar points around that query point, and then we sample those k features. And like, just to give perspective, on an average scene, we have total radar points post filtering, which are around the scale of 500, and the value of k we chose was 10. So we just collect all the 10 features from the nearby points from the query, and then we aggregate all the features of radar as well as images through this green box. And it is not a simple aggregation. We have some like basic machine learning layer to fuse those features. And then at this stage here, we have encoded our queries with images and radar points. And then we run it through again iteratively, and with every iteration we are refining our queries, and experimentally we have seen 6 is a good number for this kind of setup. So yeah, this is one of the approach how we are doing this. And another approach how we do this is using another, like, it has a very similar baseline, but it is a little different approach. And this paper is accepted at IEEE CAE. What we are doing here is, like, similarly up to here, we have a very same backbone and encoders using FPN. And so instead of putting our radar detections directly into our decoder, we pass radar detection as an input to our decoder. So here, like, as you know, like, data style architecture has some pre-trained vision queries, and we include those vision queries along with radar detections. And radar detection are nothing, like, they are just like 500 post-filtered point cloud from radars. And we have a 3D location of every single radar point. So we can encode those 3D points into a 256 or 120 dimensional queries. And we pass those 2 set of inputs to our transformer-based decoder. And this transformer decoder, it has 2 attention layers. It has self-attention as well as cross-attention. So as you can imagine, this kind of double query system has some redundancies, and we rely on the self-attention layer within the transformer decoder to take care of those redundancy, because self-attention layer can basically interact with it lets every single query to interact with every other query so that there are no duplicate detections. That is why this kind of approach have also let go of NMS to remove duplicate detection. And yeah, it's relatively simpler. So we just use those vision and radar queries to detect bird's eye view boxes, and there are two heads on the decoder, the classification head and regression head, and we predict those labels respectively. Yeah, this is all I had. Thank you, everyone, and I can take questions now. Yeah, go ahead.
So why did you choose the bird's eye to do the fusion of the
not, for example, some other.
Like you mean like compared to perspective or
The bounding box.
oh, I see.
The bounding boxes and but not in the person.
Yeah, so this is actually what we have already done, the boundary boxes fusion. And so that approach, this is part of late fusion in the middle. So this problem, this kind of fusion has an issue because we are not letting vision features to interact with radar features before making the prediction. So for example, like let's say if there's a moving object and radar can easily pick it up, but we don't get enough vision features. So there might be a, there would be a conflict of confidence values between radar prediction and vision detection, and we don't know which one to trust. So for example, like one of the other keynote presenter was showing the autonomous F1 car, and they mentioned the same thing. We also suffer through the same problem. So to get rid of those confusions, like if one of the sensor modality is giving a very high confidence detection and the other one is not, so to get rid of that confusion, we are predicting a single confidence value from using both the features together. So it is more of a research problem right now in our company, but this has already proven to be better. Now, the only thing which is not letting us deploy this kind of a thing is the runtime.
And how do you do the spatio-temporal alignment? Because it was not shown in the diagram.
Yes, so it is not part of this paper, so I can't talk about that. Yeah, sorry, we have a very strict IP policy, but yeah, we do it. Yeah.
And my final question.
Yeah.
The data sets for your training pipeline, are they publicly available? Or?
So we have Nuisance available. It is a subset of our internal data set. And yeah, but it is very similar. Like it has, like Nuisance has 6 camera setup. We have 8 camera setup. And yeah.
For example, if someone would like to build upon something like this, would they have their data set somewhere?
No, that is a proprietary data set. Yeah, but it is very similar to Nuisance data set. And yeah, Nuisance, as you know, like it has radar points as well. That is probably one of the only data set which includes radars. Yeah. Yeah, go ahead.
So have you done any comparative studies with camera, LiDAR, fusion, PV, perception, and have you like learned any lessons on short of vision, radar, just compared to vision?
Yes, so we have compared, so that's exactly what we have done to evaluate this model. We wanted to beat LiDAR. We can't as of now, but so majority we are falling behind on the orientation of the boxes because radars don't give us orientation. We just have to do it with vision. So there's no supervision at all with the sensor fusion. And then another thing is the depth estimation of all the boxes. So camera can see every single object which LiDAR sees, but it's not good at predicting the right depth for them. Radar helps them, but it's not still at the same level as LiDAR because LiDAR is giving all the information in the input space as well. Like, so we don't really have to predict anything. Like you can even like do a simple clustering of those point clouds and get the right depth. So yeah, so that is one of the other ways, but we have a very high recall system. So we can detect every single object, but not with exactly right regression parameters. Yeah. I've got one question on the Zoom chat from Kevin Patel. Is there any plans of using a 4D radar sensors for camera plus radar fusion? So yeah, we do have a plan for it and we are working on it. I can't share more details on this as well. We don't have any public IP for this yet, but we are working on this.
Last question.
Yeah.
Can you name some use cases when in your studies, when it was better to use early fusion, late fusion, and deep fusion? What scenario was it better? Or is it one that also forms all of them? Because it's clear that, for example, late fusion consumes lower resources than
deep fusion, right?
And has shown throughout the time that it is more reliable.
Late fusion? No, I mean that can be arguably wrong as well, but yeah, late fusion is robust because it is very easily deployable. We are not doing any feature level fusion early stage. And yeah, so for example, yeah, so in general, like we track our performance on the PR curves. Like we look at precision, recall, max F1 scores, AP metrics, and so like late fusion don't have a very good recall system because we are relying only, like it's very hard to tune like which confidence to trust, which confidence to not. And like as you know, autonomous vehicles, they are fast moving robots which have like vulnerable pedestrians and bicyclists on the road. So our target is to build a higher recall system rather than higher precision system. And late fusion was suffering on building a higher recall system because some of the features we expect from the camera and some of them are from radar, and there's no right way to fuse them. And yeah, that is one issue. And we haven't implemented any deep early fusion thing. Like early fusion is also very hard to do because radar is very sparse and cameras are very dense. LiDAR is like intermediate between the two. So it's easier to do early fusion with those, which we are already doing that. But yeah, we are doing early fusion with LiDAR, radar, and LiDAR and camera, but not with camera and radar right now. Yeah, go ahead.
That was actually also my question. Respect to if you think this will eventually become a thing with camera and radar, I would think it's just not the way because the modalities are so different. That's what makes the characteristics.
You mean early fusion?
Yes.
Yeah, so I have very limited knowledge on this because, like, to be honest, I haven't explored that. And also it's very hard to, like, one thing I can see that doing is, which we have done that in our analysis and then we ruled it out, was to build like post-process the radar points to build a radar imagery and then fuse it together, like just simply maybe even concatenate the two images together and pass it through a regular network. So that one we have explored, but then the issue it had was radar images was like, it's still a post-process step. It's not part of network. So it depends a lot about our hand tuning, and then it is time consuming, expensive thing to do right now. And the other thing was getting a radar images also adds to our latency network because images we are already getting it and we have to get radar images as well. So that thing created an issue. So we explored the deep fusion over that. But this, like, we have one team who is exploring this idea. So our team brings we do research as well, but we also bring all the network to our cars. But we have a research standalone team which just do the research. We work with them to evaluate any very high technical researchy topic. So that we have explored that through that team.
I mean, specifically with the 4D imaging radar trend thing.
Yes. So 4D imaging is, I think, something which every autonomous car is exploring right now. So yeah, even we are, and hopefully we'll get there. Yeah. Right. Yeah.
For your presentation, as I understand, the most high signature features are based on the camera.
Yes.
So because the GNA is only applied to the camera images.
Right.
So as I understand, the radar is used as some supplementary features for the network. But when, for example, if there are some adverse weathers, like the snow weather,
right,
then there should be the camera images that are sometimes not available.
Yeah.
So in this case, we should consider the sensor availability of the camera and the radar. So is there some plan to do with those sensor availability problems?
Right. Yeah, we are doing that. So we, in our like sensor fusion networks, we do a dropout training as well. For example, in certain cases that we don't have a particular sensor modality, and that includes not just like to entire modality, but also to a single camera level information. Like we have 13 cameras, and like there is a very common scenario where we drop one of the camera frame. So we do that training, and we have a network which tells. So for example, like we can also essentially just produce any dummy values from the cameras and still try to process that through a network. So we have a secondary network to predict that the sensor is not giving a dummy values, but it is giving an actual value. So if that it's just a Boolean network. So if that network tells that these are dummy values, then we only look at the radar detections. And radar is the only sensor which can detect through the adverse weathers. But so that is like we try to pick those deployment areas which don't have very bad weathers. Like we are deploying in Los Angeles and Vegas, so we don't deal with that. We have previously started off with Pittsburgh. That's where I am from as well. But we are not considering adverse weather cities at this stage because it just makes the problem even more hard. Yeah. Yeah. Yeah.
You said you are sharing the motivator, which the height information is available. But
which information, sorry? Oh, height information, right? Yes. Yeah.
So the problem is the density of the radar is one of the most important issues because we usually for the radar or for the LiDAR, usually the network usually recognize the shape. Yeah, it's the shape is the but if there's the density is really sparse, then it's really hard to recognize the shape.
Right.
So
yes,
is your motivator capable of making the density parser or denser?
So we are not developing a 4D radar in-house. We are using external companies to do that. I cannot name the companies right now, but we are working with them to write a filtering algorithm and make the image dense or not based on their input and our data set. So it is an ongoing work, but yeah, we definitely look at that. So currently we are also not exploring the early fusion option at this stage. It's more of a research problem than an application problem right now. That's what we feel. That is, yeah. So yeah, there is no much public work that we can share right now though with what we have an output because it's still a very ongoing thing. But it seems like it is very like possible future to do this because like a lot of companies have been doing merging because like we are kind of in a state where we have to show that we have a good business model as well. It's not just a research problem anymore. So, and radars and cameras are one of the cheap sensors to meet that, to show that business possibility with this. LiDARs are a little expensive and also it's a big chunky as well to put it on the car. Yeah. Okay. Any more questions? Yeah, thank you everyone. Thanks for listening.
Hi everyone. My name is Alexander Swerdlow. I'm a student at University of California, Los Angeles. And first of all, thank you so much for inviting me to talk. It's an honor to be here. And today I'll be talking about generating vehicle camera perspectives from a bird's eye view. And so for a little bit of background motivation, as many of us know, safety critical scenario generation has been well studied, but there's often a disconnect between the scenario description itself and how that can be used to create and evaluate a full autonomy stack. And so today, my talk is focusing on the perception aspect of this and how we can connect the scenario description to generating synthetic sensor data. And so traditional approaches to this problem often use complex simulation engines. So for example, Carla is a popular approach, which is based on Unreal Engine. They combine that with model-based scenario generation and then fill in the gaps of what's not described with rule-based approaches or random selection from a handcrafted library. And so connecting scenario generation with diverse and realistic perception is a really challenging task. And so there's sort of a natural question is, can we have the best of both worlds with both diversity and fidelity? And so how do we fill in sort of those gaps that aren't described by scenario generation? And so as has been talked about multiple times today, and many of you are familiar with, bird's eye view representations have been found to be useful for a variety of predictive driving tasks. So detection, segmentation, forecasting, and more. This is because it contains all the information required for decision-making, but nothing more. And specifically in the context of perception, it leaves out a lot of important things like lighting, weather, background, etc. And for a predictive task, this is perfect because we strip all that away. We only get what we need for decision-making. At the same time, generative modeling architectures, GANs, autoregressive transformers, diffusion models, these have been proven to be successful for, as many of you are familiar with, image generation, but also for the task of scenario generation. And we believe that BEV representation can serve as a concise, like intermediate format between scenario generation and image generation, because it provides just what's needed for decision making, but it leaves out the parts where a image generation model can fill in terms of background scenery, the different styling, weather, etc. And so it sort of is a minimal constraint on our generation, and that's a good thing in this case. And so with that motivation, we present street view image generation from a bird's eye view layout. This work was with myself, Rensheng, and Professor Zhou. And in this work, we proposed BEV Gen, which is a conditional generative model that synthesizes a set of realistic and spatially consistent images that match the layout of a traffic scenario. And so here, just to give a high level sort of overview, is we go from the left, which is a bird's eye view layout, and we generate what's on the right. So that's our inference pipeline. And we see that we evaluate on two different data sets. The top is on new scenes and the bottom is on Argo verse 2. And we see how, and we see the correspondence between the cars in the map and the cars in the images. And it's a little difficult sometimes to visualize the exact occlusions, but we see there's generally consistency if you sort of peep. And so BEV Gen is based off of a VQ-VAE architecture with a patchwise GAN component from VQ-GAN. And so there's two training steps that we have. The first is the leftmost part of the diagram. And that consists of learning an autoencoder on both images and on our map representation. And then in our second stage, we learn an autoregressive model that is conditioned on these indices of our map, and then generates a set of multi-view images. And we also develop a variant of this model that is significantly faster. It has slightly worse performance, as we show later. And in order to do this generation, we use a couple tricks. We show that the decoding order does have an impact on performance, and specifically, we find that center out decoding, so decoding from the center of the centermost image, helps performance. And a second big trick that we use that I'm not going to go into too much detail because is actually was very directly inspired by a speaker, Brady, who hasn't spoken yet. So I'm going to let him cover that. But that is having positional embeddings for both the image and map tokens, and specifically for the images, embedding the intrinsic and extrinsic information into a direction vector, and a very similar approach for map tokens. And that helps both with correspondence between the two, and it also helps allow us to do additional augmentation, and so we can vary, and so we can crop and modify these parameters. And then Next, I'll cover the second technique we use, which is a camera bias in a little more detail. And so this has a very similar idea where we have a bias for each element in our attention matrix. And so this is a multimodal attention matrix because we have both map and image tokens. And what we do is we have a cosine similarity between these direction vectors, regardless of modality. And then we also have a learnable parameter for each token. And this is applied at each attention layer because it's a very simple constant bias matrix. And so we have some more qualitative results here. On the left are generated images, and on the right are real images. And we can see that they look like they're in totally different cities, but the cars are generally in the same place. We can see in the middle image that the sidewalk is in the same location, and there's very clearly a lot of consistency between the two. And so for some quantitative metrics, we look at how the performance of the spatial embedding, which was the first thing I mentioned, and then the camera bias, as well as our choice of decoding order. And we see a very steady improvement by using these methods. And we also see an improvement in the view consistency score, which I will discuss in a second. And we evaluate with BEV object detection on both road and vehicle categories. And the performance on vehicle categories is relatively poor, and it is something that we hope to improve on future works. But it is this is the first work on this task, so we include it as a baseline. And we also show the results with some by using our synthetic data for data augmentation, and we also see small but meaningful results. So next, I'll discuss the view consistency score and why that's relevant. And we were looking at how to determine whether overlapping views were actually consistent or not quantitatively. And so we came up with this metric that looks at overlapping portions of two images. And what we do is we extract an overlapping portion of that window, and then we perform a feature matching. So we find correspondences between these images. And we use the sum of these confidences, and we average that across all windows. So for a single instance in time, we average it. And for that instance in time, we obtain this metric called VSC. And so here are some other applications of our model. We can perform, given one view, sort of extrapolate to other views. And we also show results with frame-by-frame generation. So there's no temporal consistency here, but it does show the consistency between the map and the images. So just a quick video. And we see that the background changes in subsequent frames, which is exactly what we want. And for some future directions that we have, there's a long list of things that would be really beneficial in a production scenario. So temporal consistency is a big one. Control over scene properties, weather, time of day. These are all things that we included in our initial work, but are very possible with our architecture, and would be helpful. And then also, one weak point is generation of small and rare classes, and that's something that we hope to improve in the future. We also demonstrate, here's a very short snippet with video generation. And it gets worse, as the time window increases, which is expected, but it's more of a proof of concept. And we also show this snippet shows some like interactive generation where we can modify the position of, for example, a specific vehicle or multiple ones, and then in an interactive way, and then show the generated image. Finally, some takeaway thoughts. First is that there's significant benefits from directly connecting scenario generation to image generation, both in image diversity and reducing the pipeline complexity. So a lot of simulator pipelines can get very complex, and this is a little more straightforward. And we've shown that this transformation from BEV to perspective is in generation is possible, but we still do need more work before it reaches production quality. And then lastly, verifying these results is a challenge in itself. So it's we can qualitatively look at these images, but just using traditional image generation metrics are incomplete. And that's why we introduced the view consistency score, but we also believe that more metrics will be needed in the future for a more thorough evaluation. And that's all I have. And thank you so much for listening.
Thanks for the talk, Alexander. Xinshuo, you want to take over?
Ravi, we have a question here.
Go ahead.
It's about time consumption, please. Since this is a frame-by-frame approach, which actually is a problem of time, temporal consistency, as you said, how much is it consuming? And the second question is about objects coming from occluded areas. How do you generate consistent images taking into account occlusions?
I didn't quite get the first question. What was that about performance?
Time consumption. That's it.
Time consumption. So like how long it takes to generate an image versus video.
And the second question was about occluded areas. How do you generate?
Great question. So for the video demonstration that I showed, this was a two-frame model. We generate one frame, then the next frame, and then we shift the window back. So in that sense, this very much depends on the attention mechanism used, because attention is generally quadratic, but there are like more efficient ways of doing it. And so it can be much slower, but there is a whole body of work focusing on this sort of video generation, making it more efficient. That's not something that we cover in this paper, but I do think that it's reasonable that one would be able to get reasonable results with this technique. In terms of occlusions, this is also something that we left that to the model to handle. We did not see examples in which the occlusion was sort of done incorrectly, and specifically one example is if you look at the bottom, there should be a car in front of the center car in the middle, which we don't see, which is a good thing. We sort of see a little bit on the side of the car, but that's it. And so at least in this specific case, it worked. But another approach, instead of trying learning it implicitly, would be to have our bird's eye view map handle occlusions itself. So if we did have some notion of height, we could do it that way. But those are sort of the two ways that it can be done with this approach.
Are there any other questions?
Yes.
Yeah. Go ahead.
So I suppose that images are used, generated images are used for training purposes. Did you check the behavior of these synthetic images in training, segmentation or self-supervised depth estimation model in comparison with training on real images?
So yes, so that was the so the result on the bottom left hand corner. So the results were, this was on cross-view transformers, which actually Brady's going to present on later. But this was the result by including synthetic images. So as I said before, the result wasn't a significant, wasn't a huge improvement, but it was reliably a small bit better.
Okay, so the first row is from the your. So I don't understand. Please explain the table 3.
Sorry, what was the question?
If you can explain table 3, please.
Table. Oh yeah, sure. So the first was so the top level was training this model on new scenes with the
only real images. First row.
What?
Without augmentation, and the second one is with augmentation, and augmentation means synthetic images. Okay.
Yeah.
Actually, I do have a follow-up question here regarding this augmentation.
Yeah.
I mean, I can understand that with some augmentation, you get slightly better performance, but out of curiosity, do you have some experiments without using the real data at all? Like, I just wondering how much the domain gap is, like how much you can really reconstruct the original data.
That's a really good question. We didn't train on just that. My guess is that with the current performance, it would be significantly worse if you only use synthetic data. Obviously, that's something that we'd hope to improve in the future, but we didn't actually run that experiment.
I see. Okay, thank you. Are there any other questions from the audience?
No.
Okay, sounds good. Thanks again, Alexander, for your wonderful presentation. So let's move on to the next speaker. Here, our next speaker in our agenda is Adam. Hi, Adam, can you hear me? Yeah, can you try screen sharing?
Okay.
Yeah, in the meantime, I will introduce you. Yeah, so our next speaker, Adam, is a postdoctoral scholar at Stanford University. He recently completed his PhD at Robotics Institute, where I came from as well, from Carnegie Mellon University, where he worked with Katerina, and his research interested in computer vision and machine learning, particularly for 3D understanding and fine-grained tracking. Today, I think he will talk about his recent work on BEV perception. Okay, so now let's welcome speaker. Adam, the stage is yours.
Great. Okay, thank you very much. Thanks for having me. It's always nice to see some familiar faces. So today I'm going to talk about a paper called Sample BEV, What Really Matters for Multi-Sensor Bird's Eye View Perception. I showed this paper at ICRA just a couple days ago, and I've added a few details here, which I'm hoping are going to be interesting to discuss. So to perform driving-related tasks, autonomous vehicles need at least a bird's eye view representation of the 3D space surrounding the vehicle. Oh, by the way, can you see a full screen video right now? Or
yeah.
Okay.
Yeah, I can see a full screen, although it's like in a very zoom-in version. I'm not sure if that's what expected.
Okay, I think that's probably fine. So we're looking for this bird's eye view understanding of the scene. And the challenge really from the perception side is to acquire this kind of representation using the sensors mounted on the vehicle itself. So that sensor platform typically includes radars, cameras, and sometimes a LiDAR unit. And considering the cost of high density LiDAR compared to the other sensors, there's great interest in building perception systems that do not rely on LiDAR. So recent research has focused on developing camera-only methods, where the focus is usually on just innovating new techniques for lifting the features from the 2D image planes onto the bird's eye view plane. And here I've organized some results from the past 2 years of work on this problem. And these methods differ in a variety of ways, so it's a little bit difficult to compare the curves or the bars exactly, but we can see there's very steady upward progress on the key metric here, and it's remarkably fast, right? It's going up here 14 points in just 2 years. That rapid progress has been attributed to the development of better and better 2D to 3D lifting strategies, as I mentioned, because that's been the main focus, main driver of the work. But we've observed in this paper that other details have shifted at the same time, making it unclear what really matters for the top performing methods. So is it the lifting? Is it the batch size? Is it the resolution? Is it the backbone augmentations? Or is it something else? So in this work, we're first going to try to clarify the high impact factors in the design and training protocol of BEV perception methods. And second, we're going to make the point that results can be substantially improved by incorporating input from radar, which typically goes unused, despite being readily available both in datasets and in the real world. So before I talk about methods, I want to try to talk a little bit about the inputs and outputs, just to make sure that we're on the same page. So in this work, we're dealing with the new scenes setup, which involves 6 cameras and 5 radar units and 1 LiDAR unit. The camera data is very dense and high resolution, but of course it's only 2D. The radar data is sparse and noisy, but it's robust to weather conditions, and it can give you metric distance measurements, along with some other information like the velocity of each return. The LiDAR data gives you a fairly dense 3D point cloud, which is great for tasks like 3D object detection, but typically it comes at a much higher cost than the radar or camera data. The output that we're aiming for is bird's eye view vehicle segmentation. So we evaluate this by measuring the intersection over union of our estimates against the ground truth. So as I mentioned, recent research has focused on the camera-only version of this task, and the architectures across most methods are actually very similar. So they begin with ResNet operating on the RGB images. So this is shown at the left side of my diagram here. And this produces a low resolution but feature-rich representation of each camera view. And that ResNet is usually very deep. It's like a ResNet 101, for example. And then they lift the features onto the bird's eye view plane, and they differ in how they lift. And finally, once they get to this bird's eye view feature map, they process that with another ResNet, which is typically cheaper, like a ResNet 18, and the head of that network produces the vehicle segmentation. So I'm going to try to step through now how exactly the methods are trying to lift from 2D to 3D. So here we have a method with MLPs devoted to converting a vertical strip of image features into a flat strip of bird's eye view features. This is one of the earlier papers. Here we have a very popular method which estimates a distribution over depth for each pixel, and they use this distribution to decide how much each feature should be propagated along its ray. And here we have a more recent paper, which actually just came out as we were finishing up our ICRA submission, which collects contributions from image features using deformable attention. So every voxel has a deformable kernel with learnable offsets that deviate from the projection center to hopefully gather up multiple pixels that can contribute to each voxel. So we're going to compare all these with a fairly simple method, which just collects features through bilinear sampling. So the idea here is that for each voxel, we take the center of the voxel as a 3D coordinate, project that into the camera viewpoints, and bilinearly sample from the features there. So that fills up the entire volume with image features. So we find that in apples-to-apples comparisons across these lifting methods, first of all, parameter-free lifters like our bilinear sampling are still pretty competitive with the learned alternatives. We also observed that the gap between the best method and the worst method is only about 6 points. So this is a little bit surprising, right? Because we are seeing this 14-point gain in accuracy over 2 years, apparently due to lifting. But when you match all the settings perfectly and just focus on lifting, you only get the 6 points instead of 14. So it's useful to slow down here and compare the details of these splatting-based methods and the sampling-based methods. So lift, splat, shoot, and in fiery, which, as I said, are very popular methods, they're represented on the left half side here, where for each pixel, they're going to push it along its camera ray into the volume. And for each voxel that it intersects with, they add a bit of the feature vector to that voxel, weighed by the depth distribution estimated from the image. Our own bilinear sampling method and also BEV former are represented on the right-hand side here. And what these methods do is, for each voxel, they pull a feature from the image feature map at the projected location. So as you might be able to imagine, like if you simulate these lifting methods in your head, they behave differently at close and far distances. So close up, a splatting-based method, or shooting, you can also imagine, is going to do slightly better, because if a voxel is hit by multiple image features, it receives features from all of them. For medium and far distances, though, splatting falls behind. And this is because if you're shooting along the rays, you can imagine that you might sometimes miss a voxel that's far away. So sampling flips this around by saying that every voxel gets to pull a feature from the image. And that way, every voxel ends up with a good feature inside. So coming back to the big picture here, lifting only got us about 6 points of performance and doesn't match the 14-point rise that we're trying to explain. So in the next experiments, we're going to use our simple bilinear sampling architecture and explore the details of the training setup. Our first big finding is that batch size, when you're training the model, the batch size that you use has a huge effect on the test time performance, where training with larger batches reliably increases performance. So the earlier papers lived somewhere on the left side of this curve with batches like 1, 2, or 4. But if you increase that all the way to 40, you can improve by 14 points. So you might not have the memory to do this like in a feed-forward pass, but you can accumulate gradients to get batch sizes this large. Input resolution also has a very big effect, with the higher resolutions generally being better. So here we're talking about the resolution of the RGB images before they go into the first ResNet. The model also slows down as you increase the resolution here, because that ResNet is the most expensive part of the model. And also, you can notice that the results drop at the very highest resolution, probably because when the images are this large, the object scale is no longer consistent with the pre-training. So it's less effective transfer. Turning to the backbones that we're using. So backbone at the first stage of the model, where you're converting the RGB images into feature maps, we find that deeper backbones typically perform better than the shallow ones. But this isn't night and day, right? This is only about 4 points difference. Augmentations help as well, but to a lesser extent. So these are like 1 or 2 point differences, where if you're doing copying and resizing at the images, you're randomly rotating your coordinate system to center on different cameras, or you're randomly dropping out cameras, you're not going to vastly change the performance of your model, but you might reduce overfitting a little bit. Turning our attention to radar, we note that prior work has reported the radar data in new scenes in particular to be too sparse and too noisy to be useful. Visualizing the data ourselves, we can see that it is indeed much sparser than the LiDAR, but it gives us very useful hints about the metric scene structure, which we think should be useful. So looking at this visualization, you can sometimes see like where the edges of the road are. Some of the dots correspond to cars, some that correspond to buildings. It's useful to have this information. At least that's our hypothesis. So the way we're going to try to use this radar information is we're just going to concatenate it as an additional feature channel. So after we lift things to 3D, we have some feature length that depends on the input ResNet. We're going to add just a few more channels. So maybe one channel if we're using the radar as occupancy, or multiple channels if we're going to use the velocity information as well. So with that simple fusion strategy and our parameter-free lifter, we obtain an 8-point improvement over our camera-only model. So for reference, we also compute results using LiDAR and find that that's 8 points further ahead. So that means that radar is giving you about half of the way that you'd get from LiDAR. And it's also apparent that the sensors are capturing different information, because if you use all 3 sensors, you get another point boost. So there is some information in radar that's missing from LiDAR. But overall, our reading here is that the more metric information that we have, the better. To maximize the benefits of radar, we found that it's useful to use all additional metadata associated with each return. So this includes the velocity that you get from the Doppler effects, and also the confidence and validity estimates that are just packed in with the sensor returns, which I think computed using heuristics defined on the velocity and confidence. It also helps to avoid outlier filtering to give you denser data. So actually new scenes, like by default, is filtering out some of the radar returns, which is supposed to improve your results, but actually that's the opposite is happening. It's better to have the denser data, even if it's noisier, because at least the hypothesis is that it's about capturing more metric information, and then the network is probably okay at denoising all on its own. Finally, it helps to aggregate the data across multiple radar scans, again, increasing the density. So here what we're doing is just aggregate the radar that we get from time step t with time step t-1, t-2. And so this kind of effect has been shown with LiDAR before, but we're showing that it's also consistent with radar. So our camera-only method with the parameter-free lifting outperforms all existing work, at least at the time of publication, which we think demonstrates the strength of our training setup. Our radar model is a pretty wide margin above the rest, which demonstrates the importance of incorporating metric information wherever it's available. As we incorporate more sensor data, we do better. In the context of related work, our results suggest that getting certain implementation details right seems to outweigh the contributions provided by the sophisticated lifting strategies pursued in the other methods. And furthermore, our results demonstrate that radar, although sparse and noisy, provides a substantial boost to performance, helping to bridge the gap between the camera-only and LiDAR-enabled systems. So before going to future work, I'll just summarize our key findings, which is that batch size and input resolution have a huge effect on performance, especially compared to what people thought was important, which was the lifting strategies. And we also show that camera radar fusion can give you a very large performance boost. So it's useful to use your metric sensors if they're available rather than leaving them aside. So now for future work, I want to try to describe a few things that we mentioned in the paper and a few that we didn't. So here's one that we didn't mention, where we noticed that there's a pretty big gap between our training accuracy and our validation accuracy. So the validation accuracy is the one that everybody reports, right? So that's our state-of-the-art 47.4 there on the slide. And when looking at this kind of big train val gap, it's kind of appealing to think of it as some kind of distribution shift issue. But it's not the case here that we're training and testing in different cities or in different weather or anything like that, because it's just the new scenes train val split. So it's more likely this is just overfitting. So we have a very data hungry model, and it's hard to come up with enough annotations and augmentations and regularizations to overcome this train val gap. But if you could, you'd have a huge improvement in performance. Another aspect to look into is the fact that we're learning all of our representations purely from supervised training. So in autonomous driving, we don't yet have self-supervised representations that are better than the ones that you get supervised. And that's a market that's been reached in image-based models like Dino and Dino V2 recently, where you can show that it's better to self-supervise in ImageNet, for example, than to use actual ImageNet labels. And that's a very powerful result, which we don't yet have for driving. The closest thing we have is that you can show that self-supervision is useful as it'll contribute some missing priors or regularization, but we don't yet have this kind of result where it's actually better to self-supervise. It'd be really nice to have that. Speed and resolution are also worth thinking about. So for driving, very fast runtimes are critical. So this might involve exploring different backbones to potentially run faster without sacrificing the inference power, which would hopefully shift this entire curve I'm showing onto toward the left side of the curve, or left side of the plot. So you're shifting the entire curve. And at the same time, it seems clear that we're leaving some performance behind, especially at this highest resolution. So for very far away objects, using the highest resolution imagery is critical, because to even see them with human eyes, you need to use the full resolution images. So it'd be good to develop backbones that can make use of this data appropriately. Lastly, it's useful to think seriously about time. So I think there was a question at the end of the last talk about temporal integration. And a detail to notice in this work and in similar ones is that the estimates are a little bit flickery. So this the third panel at the top row here is showing our estimates. You can see sort of objects flickering on and off. And this is because the model lacks temporal consistency because it's operating frame by frame. And the reason we didn't include a temporal consistency module here is that we didn't see a big gain from including it. So we only got something like a 2 or 3 point boost to performance, which is similar to the gain that other people reported also, which seems like it's too small, right? You should be able to gain quite a bit of performance by knowing that the world is stable and by knowing that the state at time t is going to be very similar to the state at t-1. But we don't yet know how to do this. So that's it for my talk. I encourage you to look at our website to get some more qualitative results and also to try our code, which is on GitHub. Thank you.
Thanks, Adam, for this insightful presentation. So let's now move into the question. Are there questions from the attendees? Feel free to shoot.
Have really a quick one. So excellent talk there. Was wondering in the plot where you showed pulling or sampling versus splatting methods, is there a way to determine at what distance you should switch from one method to the other? You did say that the combination should work better, right? What criteria would you use?
Right. Well, you could, for example, use this you could just measure performance at the different distances, maybe decide what to do. It might be also interesting to think about taking multiple samples per voxel, maybe according to the image density at that distance. But I think we still need good methods to be able to get the best of both worlds.
Thanks.
I do have one quick question. If no questions from the audience. And also, one of the interesting points you brought up is the like in the current field that we're missing the use of self-supervised foundation models for driving, right? So I mean, this is kind of obvious, and because it has been demonstrated very powerful improvements in many other domains. So what do you think the reason is, like for driving, like why we don't have it so far? I mean, maybe it's just like people are developing it, or you may think there's a fundamental reason that we're missing it. Like basically, what's your thought on that?
Yeah, that's a good question. So I think people are trying, I think they're trying very hard. Maybe they're in the same boat as me, as like where they're getting some results, but they're not amazing, and so they're holding back a little bit, and they focus instead on just like getting some minor improvements from self-supervision. But I mean, another aspect here to consider is that like in driving, we do have a lot of things that we need to do that have very concrete definitions, like knowing exactly where all the cars are is a pretty clear task. Knowing where all the lane markings are is a very clear task. And not using the labels for those tasks would be a bad idea. So maybe people are just trying to focus on the practical aspects of the problem, which they think are going to maybe outweigh the contributions of some feature learning, where you're not always sure what the feature learning is going to end up with, right? You don't know that you're going to learn cars if you're doing fully unsupervised learning. So I think there's some interesting trade-offs there for driving.
I see. Okay, that makes sense. But that's also kind of related to the data for this self-supervised learning, right? So for example, imagine like what you're saying is that, okay, in the data they use to self-supervise, they don't include all of those kind of very useful information for driving. Then it's clearly need to suboptimal performance compared to the case where you're using this kind of clear definition or clear information that is useful for driving. So if we include that data in some formats for like in the way that we're training Dino or LV2 as today, then maybe we're able to do it. But yeah, I think I get it. Okay, so yeah, are there any other questions from the attendees? I don't want to occupy all the time here.
Maybe one question from my side, from the audience. You mentioned at the very end of the talk that you also looked into temporal, like integration of temporal aspects, but it only gave a minor improvement, which was like a kind of counterintuitive. And I agree that it's very counterintuitive because if you take into account multiple time steps, you should avoid occlusions much more easily. So I was wondering if you have like hypotheses why that could be, that it was not giving a bigger improvement than expected.
Okay, yeah, that's a great detail to talk about. I think the key issue is maybe alignment in space, where like for the static part of the scene, it's fairly easy to align things in your state representation just by using the ego motion, right? You just warp things from t-1 to t, and then it's like you'll already have a pretty good estimate for the current time step. But for everything that's moving, which is, by the way, the most important part of the scene, it's not easy to do that kind of alignment. So you end up with, you're propagating a state from t-1 that doesn't actually line up with the current state. It's not where the objects are. It's maybe even confusing. So it feels like there's some kind of chicken and egg problem where you need to be able to know where the objects are, need to be able to track them and forecast to be able to correctly infer the state for time t. But of course, knowing the state for time t would also help you do that for state t+1. So it's difficult to align things correctly in your spatial map when they're moving.
That makes sense, yeah, thanks.
Okay, so in the interest of time, let's just stop here. And thanks again for Adam to give this wonderful presentation. Now let's move to our next speaker. I think Yue, are you there?
Yeah, I'm here.
Okay, sounds good. Yeah, so maybe you can start testing your screen sharing, and then in the meantime,
Yeah,
I will
sure.
introduce you.
Yeah, let me share my screen.
Yeah, so our
Okay,
next
can
speaker.
you see my screen?
Yeah, I can see you.
Okay, sounds great.
Yeah, it's very well. Yeah. Okay, so our next speaker, Yue Weng, is a research scientist at NVIDIA and also incoming assistant professor at USC. He's currently leading efforts to build neural field representation for robotic and autonomous driving. His research interest lies in intersection of computer vision, computer graphics, and machine learning. And today, Yue will give a talk around the topic of scalable autonomous driving. So let's get started, and the stage is yours, Yue.
Yeah, thank you, Xinshuo, for the nice introduction. And hello, everyone. I'm Yue. Today, I'm very happy to share with you some efforts we do at NVIDIA towards building scalable autonomous driving. And this is teamwork. And actually, Xinshuo also contributed a lot to those works. So let's get started. So basically, broadly, there are two main architectures for autonomous vehicle today. For example, on the one hand, on the left, modular designs, which compromise independently trained modules, for example, detection, tracking, prediction, planning, and control. So this is a typical structure and that most AV companies have adopted. So because of several key advantages such as interpretability, reusability, and the feasibility to make formal safety claim. However, this architecture introduces several information bottlenecks and might give rise to integration challenges. And on the other hand, on the right, we have monolithic architectures with end-to-end learning, so which directly link perception to control, typically through a neural network, and only implicitly encode key capabilities such as agent prediction. So as key advantages, so this end-to-end architecture removes information bottlenecks, and because of that, one could argue it might achieve a level of optimality and attainable by modular architectures, so which are based on the rigid modular composition. So also, it's straightforward to scale up the performance of the end-to-end architectures when large-scale data becomes available nowadays. And indeed, we have seen a very large trend of development in end-to-end approaches in the past several years due to its scalability and also due to its simplicity. So taking the well-established color driving leaderboard as an example. So when the pioneering work, learning by cheating, was first proposed, its performance is relatively low due to poor quality of the expert and the data collection process. However, as time goes by and stronger experts are developed, and the performance of subsequent work has been substantially improved. For example, a big jump in performance happened in 2022 due to the development of transfuser and its strong expert. And also, in contrast, if we look at the popular modular approaches in the same benchmark, so the performance lags behind and does not benefit from the improved data and the expert. So does this mean that this modular approach is necessarily suboptimal, or is it just because something else? So, well, the answer is not quite. So to highlight this point, let's consider a standard decision-making setting where we want to control a system with state X. And by selecting control actions U based on measurements Z. So define the information vector as a history of measurements and the controls up to current time T. So, and consider the general class of policies that map the information vectors into controlled actions. And this problem is to find an optimal policy that optimizes average performance according to a given cost structure, represented by the function GK, and also subject to the system dynamics, represented by the function FK here. And one can show that the condition state distribution denoted by P is a sufficient statistic, and the optimal controller can always be written as a mapping from the conditional state distribution into a control action. And explicitly, this result provides a decomposition of the optimal controller into two parts. So first, an estimator which uses the current measurement and the previous control value to update the distribution P. And also an actuator which generates a control input as a function of the distribution P. And this interpretation has formed the basis for various suboptimal control schemas that separate the controller prior into an estimator and an accurator, and attempt to design each part in a manner that seems reasonable. But importantly, the suboptimality of these schemas stems from the suboptimal designs of the components, so which often does not account for key couplings, and not by the modular decomposition per se. So also inspired by this result, we conduct this suboptimality verification for the entire AV stack in the color challenge. So there's no secret sauce here. So the main difference of our design compared to prior work in modular design is to basically employ state-of-the-art perception and prediction modules that are emergent in recent 2 or 3 years. So for example, we use a state-of-the-art transformer-based architectures such as data 3D, filter 3D for detection, versus in older work, we use traditional faster RCN and the SSD for detection. And similarly for tracking, we use more recent 3D trackers such as Muter 3D, AB 3D mods, versus previous works use some older 2D trackers such as SALT or DeepSTEP. And also for prediction, we support interaction-aware multimodal trajectory prediction modules such as AgentFormer and the Trajectron++, rather than older methods that predict trajectories for each agent independently, as in PyAlert. So to verify the performance of our AV stack and popularize it within the community, we are, of course, actively participating in the color driving challenges. So the color challenge requires the participants to build the entire AV stack to accomplish this task. So it's very challenging, but also an ideal test bed for our modular stack. And currently, our entire AV stack achieved a driving score more than 84% in the standard local color closed loop evaluation, and outperforming the current best public dataset. So traditionally, this I think the previous state-of-the-art method is 58% accuracy. And also, if we replace the perception module with privileged information from the simulator, so namely, we basically replace the perception with the ground truth labels. So we achieve near perfect score close to 100. And again, this confirms that the suboptimality of modular stacks stems more from the suboptimal designs of the components rather than the composition of key modules. So how can we make our modular stacks scalable with data? So as I mentioned, modular architectures can have very strong performance as long as we carefully design all the modules. However, in practice, carefully designing and integrating modules is very difficult. So information bottlenecks will return. And simply having access to more data does not directly lead to an improved stack. So one appeal of end-to-end architecture is that it can scale better with data. So the end-to-end architecture directly links perception to control, typically through a neural network. It doesn't have any information bottlenecks, and it can be trained in an end-to-end fashion. So the more data we have, the better overall performance we can expect. But we have to give up, among other things, for more safety claims and the interpretability, of course. So a natural question to ask is whether we can get the best of both worlds in terms of architectural design, and also get modular stacks that scale with data. So that is the question we want to answer in our work. So we believe that the answer to this question is yes. And of course, to this point, we are developing modular yet end-to-end differentiable AV stacks. So that keeps the main module of a traditional AV stack and at the same time can be trained jointly from data. So thereby merging ideas from the two architectural paradigms. And the key idea is to implement existing modules in a neural programming framework, where all computation is expressed as a single differentiable computation graph. And the differentiable representation allows us to backpropagate gradients through both neural network components as well as fixed computation blocks, such as classical planning algorithms. And by this way, we can perform gradient-based learning in an end-to-end fashion. So we can improve upstream modules directly for downstream tasks. So how can we make AV module differentiable? So neural networks has already been differentiable, but we can actually also make many algorithms like planners, data estimations, also differentiable. It does require magic, of course. So we can express any algorithm as a computation graph. And as long as all operations are differentiable, we can backpropagate through the algorithm to any learnable parameters or representations of the module, similarly to neural networks. So the only caveat is that all operations of our algorithm needs to be differentiable. And unfortunately, many recent works have introduced various ideas to approximate useful gradients for such non-differentiable operations, such as approximating max with softmax, reparameterizing Gaussian distributions. And in some cases, we can approximate gradients for any black box optimization problem. And an overview of these ideas are in our earlier work called differentiable algorithm networks. And using these ideas, differentiable variants of many classical robot algorithms have been developed in recent years. So for example, for data estimation, like Kalman filters and the particle filters, differentiable planners for MDPs, POMDPs, and the graphs, and the differentiable control algorithms and the optimizers. So here I leave several, at least what I listed here is only a subset of the relevant works up to 2020, but the list, of course, is far from complete and have been growing since then. So hopefully I've convinced you that this is possible to make modules differentiable, but we are exploring is whether we can use these ideas to develop entire modular yet differentiable stacks for autonomous driving. So to make the ideas more concrete, let's focus on the prediction planning and the control modules. So this is an interesting setting given the importance of these tasks, as well as the fact that this algorithm pipeline compromises both state-driven components such as prediction module and the handcrafted algorithms such as a planning module that are typically not differentiable. So specifically in this Coral 2022 paper, we started with a fairly standard modular architecture. So it has a deep prediction model, Trajectron++, so which consumes parser tracklets for all traffic agents on the road and outputs probabilistic predictions about their future trajectories. And these predictions are fed into a planner and the sampling-based algorithm that generates a set of candidate trajectories, scores them with a handcrafted cost function, and selects the candidate with the lowest cost. And the trajectory is then further optimized in an optimization-based controller module, specifically an iterative LQR algorithm. And conventionally, the modules are developed independently, and the prediction module is trained from driving data to maximize prediction accuracy, while the planner and the controller are still handcrafted. So the key feature of our differentiable stack is that the planner and the controller algorithms are differentiable. So in the planner, we relax the argmin operation with sampling. And in the controller, we use differentiable MPC from prior work. During inference, DeepSTEP behaves exactly the same as the standard stack. But what differentiability allows us to do is, what the differentiability allows us to do is to use data at the end of the pipeline. So propagate losses through the control and the planning modules. And train the prediction module so that this module can focus on making predictions that are critical for planning. So specifically, we use to do so, we use a standard variational error loss for the prediction model, and the cross entropy loss for the planner, and the hindsight loss cost for the controller. So the hindsight cost is effectively like a reward function in RL, and it measures the plan quality in hindsight and after observing the future behavior of other road agents, which we didn't know at planning time. So we benchmark our method on the standard Yuxiong dataset. Then we compare two architectures. The first one is a standard modular stack. The second one is our differentiable stack. And the standard stack is basically trains the prediction module to minimize the prediction error. And we use the traditional planner and the controller in this stack. And the diff stack trains the predictor for a combination of prediction, planning, and the control losses. So we measure prediction performance through average displacement error, and we also measure the cost gap from theoretical optimal. So and the planning performance through the average cost of ego trajectories. So we present cost as basically a percentage difference compared to an oracle that plans with perfect ground truth prediction knowledge. So while these two stacks perform similarly in terms of prediction error as shown in the first column, this stack achieves substantially better plans. So including also reducing the average cost difference from to the oracle from 29% to almost 17%. So it's important to highlight that the two stacks perform the same computation at inference time. And the difference is that DeepStack trend is predictor to be more useful for planning and control. And in concrete examples, we found that DeepStack yields less superior predictions, which would otherwise be critical for the downstream planner. And of course, these results were just a first step. And our long-term vision is to make the entire AV stack differentiable, including perception modules such as detection and tracking. And this will unlock many new opportunities. So first, we can do a joint optimization across the entire stack, for which I shared some promising initial results just now. And beyond that, we have new opportunities for learned representations and interfaces between modules. And propagating entire across basically we can propagating the gradients uncertainty across the entire stack. And I will talk about an example for the learned representations or interfaces shortly. So the reason we are excited about differentiable stacks is not so that we necessarily want to keep all the current model-based algorithm modules in the stack, but because through differentiable computation graphs, we open up the entire design space between model-based modular architectures and the entirely monolithic end-to-end neural architectures. So far I have been talking about joint training of modular stacks with some form of supervised data. But as I said in previous slide, labeling data for autonomous driving stacks or tasks can be very expensive. So we have been incredible success of, we have seen several successive foundation models recently in generative AI. So both for image generation and the language modeling. And that these models learn very powerful representations from massive amounts of unlabeled data. So we are also very interested and now looking at the potentials of unsupervised representations learned from unlabeled data in the modular AV stacks. So why do we need learned representations? So the most common representation or interface to connect perception and planning is basically bounding boxes. So perception models output a discrete bounding box set, followed by a tracker to associate bounding boxes across time. And this paradigm is used by almost every autonomous driving pipeline. However, there are several limitations. The first, the detectors struggle with rare objects not represented well in the dataset. And second, arbitrary shapes are hard to express as bounding boxes. And the third, bounding boxes contain very little information and there is the information loss. So an interesting alternative that we can pursue is to model entire environment through occupancy workflows with learned semantic representations. And the occupancy workflows can model arbitrary objects, including objects not in the dataset, and it can provide more accurate geometry. And this will lead to better occlusion reasoning, planning, and etc. So if we augment these workflows with learned features beyond simple occupancy, we can return much more useful information from the sensors. Let's look at how we learn this occupancy representation in a self-supervised fashion from data. And at the core of our proposed method is basically generalizable neural rendering. And the neural rendering is originally from computer graphics. It provides a convenient way to link 3D representations such as voxels to 2D images that we can see. And the core idea of neural rendering, or specifically volumetric rendering, is to represent the entire scene with 3D occupancy and the color fields. Then a neural network can query the 3D representation and differentiably render every pixel by aggregating color information along each rendering ray. And we want to leverage volumetric rendering to self-supervise a learned 3D representation. And this is our motivation. And our method basically inputs multi-view images, passing them through an image encoder such as ResNet or transformer network. And the encoded 2D features are then lifted into 3D with implicit depth estimation. And then finally, these 3D feature voxels are rendered by volumetric rendering to generate the original images for the either for the current time step or for future time steps. So a very strong advantage here, and the reason why we want to do that is we can learn the 3D representation completely from self-supervision. Only what we need is only a sequence of sensor data. And additionally, we can also distill the pre-trained foundation model features into these 3D voxels. For example, we can distill the CLIP features into the 3D representation. Now, here are some initial results of our learned representations. So on the left, I'm showing a model that generates novel views and also some consistent depths and semantics across time. So as you can see, we can generate novel views, and at the same time, our method can automatically determine the semantics of each component or each pixel. And in addition, thanks to the CLIP features, the model can enable open vocabulary scene manipulation. For example, we can query the 3D representation with language prompts to remove backgrounds and only keep cars, for example. And this is done by finding the corresponding voxels to text features with feature space nearest neighbor search. And then we render the filtered 3D features. We are now working on building planning architectures and even the entire autonomous driving pipeline on top of this 3D representation. Then we envision this representation can enable autonomous driving in arbitrary domain without relying on heavy human annotations. And here I talk about some good tools we developed in the group to facilitate the research. So currently, there's no standard AV dataset format, and trying to modify existing methods to work with a new dataset can take weeks, for example. And even though there are currently many large-scale public AV datasets, and most researchers can only work with 2 or maybe 3, as they are familiar with specific map and the data formats, and have developed code bases that